Every year, humanity discards more than 10 million tons of electronic waste. Of this, hundreds of thousands of tons are televisions, packed with precious metals, complex plastics, and even deadly toxic substances. But what happens to them after they leave our homes? Did you know that inside one old, bulky television set lies pure gold, silver, and components that could become the heart of new gadgets? This isn't just recycling. This is a high-tech treasure hunt. Today, we'll show you how the most advanced recycling facilities operate and why this process matters more than you might think. It all starts not at the factory, but in our homes and offices. Old, outdated devices are collected at specialized reception stations. In developed countries, this is a well-oiled system, from dedicated containers in supermarkets to trade-in programs run by major retailers. Modern recycling centers aren't grim rubbish tips, but gleaming high-tech facilities. Their primary goal is to extract all reusable materials as efficiently as possible, while safely neutralizing the toxic components hidden inside. At large-scale operations, television recycling is organized along automated production lines, where most processes are carried out by machines rather than people. The first stage at the facility is the medical examination and sorting. Televisions are separated into three main categories: bulky cathode ray tube monsters from the past, slimmer plasma panels, and modern liquid crystal displays. Each type requires its own entirely unique approach. Then the undressing begins. Robotic manipulators or workers strip away the plastic casings. This plastic is immediately sent to giant shredders where it's ground into tiny fragments which, after remelting, will become parts for new motor cars or casings for other electronics. Metal frames and fixings are also separated and sent to their own recycling line. Once the casing is removed, the defenseless innards of the television move on to the dismantling line. Old cathode ray tube televisions receive particular attention. They can genuinely be described as environmental dirty bombs. The most hazardous component is the cathode ray tube itself. It contains up to several kilograms of lead, which was used to prevent X-ray radiation, whilst the internal surface is coated with a layer of phosphor containing toxic rare earth metals. Consequently, they're dismantled with exceptional care, often by hand, within sealed chambers. First, a specialized heated wire or laser carefully separates the front clean glass from the rear lead-laden funnel. The glass is then cleaned, crushed, and sent for recycling, whilst the lead is extracted for manufacturing new batteries. Modern liquid crystal displays are no less hazardous. Hidden along the edges of the panel, thin as spaghetti, are fluorescent backlight tubes. Each of these tubes contains a small but highly dangerous amount of mercury. That's why LCD panels are dismantled in specially sealed boxes with powerful ventilation systems. Robotic arms or workers in protective suits carefully extract these tubes. They're placed in hermetically sealed containers and sent to specialized facilities where the mercury is safely extracted and purified for reuse. The liquid crystals sandwiched between the glass layers present another challenging component. They're extracted using chemical solvents. Plasma panels require their own approach. Unlike LCD displays, they don't contain mercury, but their cells use inert gases such as xenon and neon. The panels are dismantled, the gases are collected in special containers for reuse, whilst the high-quality glass that makes up the screen is crushed and purified. Once the screens and casings have been neutralized and sent on their separate ways, the most valuable parts remain on the conveyor belt, the circuit boards. This is where the precious metals are hidden. Copper wires, aluminium heat sinks, and other metallic components are separated and sent off for smelting. The most important and complex part is processing the printed circuit boards. It's in these boards, within the microchips and connectors, that you'll find microscopic yet incredibly valuable quantities of gold, silver, palladium, and other precious metals. First, the boards are shredded into fine particles. These particles are then sent to the chemical workshops. The most common extraction method is chemical leaching. The shredded boards are immersed in special acid solutions. To extract gold, they often use aqua regia, a mixture of concentrated hydrochloric and nitric acids, which can dissolve even this noble metal. After the precious metals have dissolved into the solution, the precipitation process begins. Special chemical substances are added to the liquid, which cause the pure metals to fall out as sediment. For instance, ferrous sulfate is used to precipitate gold. This gold sediment is then thoroughly washed, dried, and remelted into small but incredibly valuable ingots. Similar methods are employed to extract copper and silver, though using different, less aggressive acids or the electrolysis method. In the final stage, all the recovered materials, gold, copper, aluminum, glass, and plastic, are compressed into compact blocks. Each year, millions upon millions of televisions are discarded worldwide, with their combined weight running into millions of tons. In Europe alone, for instance, electronic waste exceeds 10 million tons annually, and a substantial portion of that comprises televisions and monitors. This staggering figure isn't merely a statistic, it's testament to our rapid technological advancement and its darker consequences. But there is encouraging news. Year on year, growing numbers of people are recognizing the importance of proper disposal. Hundreds of thousands of tons of old televisions now find their way to recycling facilities each year, helping us preserve our air, water, and finite natural resources. Here's what the real secret we mentioned at the beginning is all about. Your old television isn't rubbish, it's a genuine urban mine. A single ton of old circuit boards contains 40 to 50 times more gold than a ton of gold ore extracted from a traditional mine. Electronics recycling isn't simply about caring for the environment, it's an incredibly profitable business of the future. We've learned to extract the most valuable resources not from beneath the ground, but from what we ourselves have created and discarded. And every time you take an old television for recycling, you're not just getting rid of clutter. You're returning precious metals to the economy and helping to make our world a bit cleaner.
Every year, thousands of quarries crush millions of tons of rock. The biggest dragline in history, Big Muskie, weighed 13,500 tons. That's like 10,000 cars. But the real star isn't the machine itself, it's the teeth. Parts weighing up to 150 pounds that bite into granite every single day. How does ordinary steel transform into nearly impenetrable armor? Today you'll see the complete cycle, from molten metal to a tooth that survives 50,000 impacts. If you want to see how they make the fangs of giants, subscribe to the channel. Here we show you the operations that tear into the earth. Big Muskie weighed 29,779,800 pounds. The bucket could fit 2 buses side by side. Bucket capacity, 4,300 cubic feet. 60 teeth on the bucket. Each tooth weighs 50 to 150 pounds. A tooth isn't just a chunk of iron, it's an engineering marvel that bites into granite day after day without wearing down. Teeth are made using 2 methods, casting and forging. Right now, you're seeing casting. Material: alloy steel with nickel and molybdenum. Molybdenum improves hardening, nickel provides toughness and corrosion resistance. Carbon content from 0.33 to 0.5%. That's high carbon steel. It's hard after quenching. Steel melts in an electric arc furnace. Temperature: 2,692 degrees Fahrenheit. 3 graphite electrodes. Arc between electrodes and metal. Power: 10 megawatts. Furnace holds 20 tons. Melting time: 2 hours. Steel gets purified. Sulfur removed with lime. Phosphorus by oxidation. Then the metal stirred in an argon-oxygen deoxidizer. Argon blown in from below. Pressure: 73 psi. Flow rate: 79 gallons per minute. Argon bubbles rise. Mix the melt. Carry gases to the surface. Hydrogen content drops from 10 to 2 parts per million. Oxygen from 80 to 20. Low gas content is critical. Gas bubbles become cracks. Finished steel pours into a ladle. Ladle lined with refractory. Melt temperature: 2,649 degrees Fahrenheit. Ladle holds 2,000 pounds, enough for 20 to 30 teeth. Investment casting. First, they make a wax model. Wax melts at 158 degrees Fahrenheit. Pour it into the die. Cool it down. You get a wax copy of the tooth. Accuracy down to a few thousandths of an inch. Models are assembled onto a sprue tree, 5 to 10 teeth per tree. The tree gets dipped in ceramic slurry. The slurry is fine zirconium powder in colloidal silica, particle size about 2/10,000ths of an inch. Dip the tree. Pull it out. Coat with coarse zirconium sand, grit size about 1/100th of an inch. Dry it. Repeat 7 to 10 times. Each layer about 1/16 inch thick. Final shell thickness roughly half an inch. The shell withstands 2,800 degrees Fahrenheit. That's the steel pouring temperature. They melt out the wax. Heat the mold to 1,500 degrees. Wax melts, flows out through openings, leaves behind a cavity that's the exact shape of the tooth. Pouring. The mold heats up to 1,800 degrees Fahrenheit. A hot mold means less thermal shock during the pour. A crane brings the steel ladle into position. The steel's at 2,650 degrees. It glows bright orange. They pour fast but carefully. Pour rate is 4 pounds per second. Air bubbles will kill the part. Metal fills the mold from bottom to top, pushes air out through the top. After pouring, they don't touch the mold. Cooling is slow, 8 to 12 hours to reach room temperature. Fast cooling means cracks. Slow means proper structure. Once it cools down, they break the shell. Sandblasting machine. Pressure at 120 psi. The sand is corundum, grit size 20 micrometers. The ceramic cracks and crumbles away. Underneath, a gray cast tooth. Surface is rough, ceramic remnants in the recesses. But the form is precise. Deviation from the blueprint is less than a millimeter. Heat treatment. First stage, normalizing. The teeth get loaded into the furnace. Temperature, 1920 to 2070 degrees Fahrenheit. Hold time, 10 hours. At this temperature, the steel recrystallizes. Large grains break down into smaller ones. The structure becomes uniform. It's like muscle recovery after a workout. The metal gets stronger and more flexible. Air cooling. Cooling rate, 90 degrees per hour. Second stage, Hardening. Heat to 1870 degrees. Hold time, 2 hours. Then rapid cooling in oil. Oil temperature, 140 degrees. Cooling rate, 540 degrees per second. The structure transforms into martensite. That's a needle-like crystal lattice, extremely hard. Hardness after quenching, 59 to 63 on the Rockwell C scale. That's harder than a file. But hardened steel is brittle as glass. One strike, crack. That's why there's a third stage, tempering. Heat to 400 to 500 degrees Fahrenheit. Hold for 4 hours. This relieves internal stresses, adds flexibility. Hardness drops to 48 to 52 units. Perfect balance. Hard enough not to wear down, flexible enough not to break. Some manufacturers use induction hardening. The tooth gets placed in an inductor. Current frequency 400 kHz. Power 100 kilowatts. The surface heats up in 3 seconds to 2700 degrees Fahrenheit. Heating depth 0.04 to 0.08 inches. Immediately cooled with water. Pressure 145 pounds per square inch. Flow rate 26 gallons per minute. The surface hardens. The core stays soft. Surface hardness 58 to 63 units. Hardened layer depth 0.05 inches. Quality control. Every tooth gets checked with ultrasound. The probe generates waves at 5 MHz. Waves pass through the metal, bounce back off defects. A crack just 0.2 inches wide, rejected. They check hardness with a Rockwell tester. A diamond cone presses down with 330 pounds of force. They measure the depth of the indent. Below 48 or above 52, rejected. Too soft, it'll wear out fast. Too hard, it'll crack. The teeth get ground down. Grinding wheel made of aluminum oxide. 80 grit. Speed of 67 miles per hour. Takes off the rough spots from casting. Surface roughness drops from 0.001 inches to 0.00012 inches. Smooth surface holds up better against wear. Rough spots wear down faster. Marking. Every tooth gets a number. Laser engraving. Laser power 50 watts. Engraving depth 0.004 inches. The number shows the batch, date, and specs. Testing. One tooth from the batch gets sent to destruction. A hydraulic hammer strikes with a force of 1,000 pounds. Impact every 2 seconds. They count cycles until failure. A quality tooth withstands 50,000 strikes. Wear test. The tooth gets abraded. Quartz sand with 500 micrometer grain size. 5-bar pressure. 100 hours. That's equivalent to 1,000 hours of operation. The best teeth lose less than 0.5% of their weight. Production numbers. A big dragline, bucket holds 4,300 cubic feet, 60 teeth on the bucket. Each weighs 66 to 150 pounds. Teeth get replaced every 3 to 6 months. One dragline wears through 80 to 120 teeth per year. Hundreds of draglines operate worldwide. 50 large machines in U.S. coal mines alone. Tens of thousands of teeth produced annually. One tooth costs $1,000 to $3,000. 60 teeth per bucket, $180,000 just for consumables. Replace twice a year. That's why every tooth must be perfect. The economics of mining depend on the reliability of these steel fangs. That's how dragline teeth are made. From molten steel to a part that chews through granite. If this was interesting, hit that like button. Write which quarries you've seen. Subscribe. We show how giants are made.
Every second, the world produces 28 million tons of stainless steel. And behind the shine of every spoon, every faucet, every surgical instrument stands one metal: chromium. But here's what's mind-blowing. chromium melts at 3,375 degrees Fahrenheit, and in the electric arc furnaces that produce it, temperatures hit 5,000 degrees, hotter than the surface of the sun. A single furnace consumes 4,000 kilowatt-hours of electricity per ton of alloy. That's as much as the average apartment uses in 4 months. 80% of all chromium in the world goes into making stainless steel. But where does this metal come from? Why are 99% of the world's chromite reserves concentrated in just a handful of countries? And what happens in that hellish zone beneath the electrodes, where ore transforms into molten ferrochrome? Stick around. You'll discover how black rock gives birth to the metal that makes steel immortal. Picture a massive electric arc furnace as tall as a 3-story building. 3 carbon electrodes up to 6 feet across plunge into a churning mass of glowing ore, coke, and fluxes. Between the electrode tips and the furnace floor, electric arcs crack and snap. Temperatures in this zone hit 5,000 degrees Fahrenheit. That's hotter than the surface of the sun. The air above the furnace shimmers with heat. Clouds of smoke and gas blast out from beneath the half-closed roof. Inside, real alchemy unfolds. Chromium ore mixed with coke melts down, oxygen escapes as carbon monoxide, and molten ferrochrome, an alloy of chromium and iron, flows to the bottom. This is a submerged arc furnace, and this is where most of the world's ferrochrome is born. The process runs non-stop. Fresh batches of ore and coke pour in from the top, molten metal and slag tap out from the bottom. A single furnace like this can pack 25 to 45 megavolt amperes of power. This is a monstrous amount of energy. An entire power plant runs just to melt the ore. When enough molten ferrochrome accumulates in the furnace, workers punch open the tap hole, a special opening in the furnace's side. And then the mesmerizing spectacle begins. A stream of white-hot metal and slag bursts out, flowing down a channel into an enormous ladle. The stream's temperature around 3,000 degrees Fahrenheit. The metal glows bright orange, almost white. The heat radiating from it is so intense that workers stand dozens of yards away, protected by special screens and fireproof clothing. Slag floats to the top and is drained off separately. The ferrochrome cools in massive molds, transforming into solid ingots weighing hundreds of pounds. These ingots are later crushed into pieces of the right size for sale to steel mills. But the process of obtaining ferrochrome, that's only the middle of the journey. It all begins with ore, mined deep in the earth. Chromite, the only industrial ore of chromium. It's a dark brown, almost black mineral with a metallic luster. The chemical formula? Iron and chromium oxide. Pure chromite contains 68% chromium oxide and 32% iron oxide. But in nature, perfect ores like that barely exist. Real deposits contain anywhere from 40 to 50% chromium oxide. Chromite forms in igneous rocks, in massive molten masses rising up from the Earth's mantle. The largest deposits are found in South Africa, Kazakhstan, India, and Turkey. These 4 countries account for roughly 80% of global production. South Africa is the absolute leader. Its deposits in the Bushveld complex contain 200 million tons of chromite. We're talking ore seams stretching for hundreds of miles and plunging thousands of feet deep. Kazakhstan holds reserves of 230 million tons. India? 54 million tons. Now, the story. French chemist Louis-Nicolas Vauquelin discovered chromium in 1797. He isolated it from croquat, a bright red lead chromate mineral. The mineral's vivid color inspired Vauquelin to name the metal after the Greek word chromos, color. Because chromium compounds produce stunning colors, greens, yellows, oranges, reds. A year later, in 1798, Vauquelin isolated pure chromium by reducing the oxide with carbon. Iron with added chromium was first produced in the mid-1800s, and the first use of chromium as an alloying element in steel production happened in France in the 1860s. The revolution came in 1893 when Henri Moisson smelted chromium ore with carbon in an electric furnace and produced ferrochrome. This became the foundation of the modern industrial method, which has evolved but at its core remained the same. Chromite gets mined both through open-pit operations and underground mines. Open-pit mining gets used when the ore sits close to the surface. Giant excavators strip away the soil and overburden, exposing the chromite layers. Then they blast the ore, load it into haul trucks with capacities up to 300 tons, and transport it to the processing plant. Underground mining gets deployed for deep deposits. Tunnels get driven hundreds of feet down, sometimes miles. They blast the ore, load it into mine cars, and haul it to the surface. The extracted ore? It's not pure chromite yet. It comes mixed with waste rock and other minerals. That's why the ore needs processing. First, they crush it in massive jaw crushers. Chunks the size of a car get reduced to fist-sized pieces. Then they grind it in ball mills down to the size of sand or even dust. After that comes separation, isolating the chromite from the waste rock. The main method for enriching chromite is gravity separation. Chromite is heavier than waste rock. Its density is 4.5 to 4.8 grams per cubic centimeter, while the rock is 2 to 3 grams. The crushed ore is mixed with water, creating a slurry. The slurry passes through jig machines, concentrating tables, spiral classifiers, centrifugal separators. Under the force of gravity, the heavier chromite grains settle faster, while the lighter waste rock is carried away by the water flow. Magnetic separation is also used. Chromite is weakly magnetic, but modern high-intensity magnetic separators can attract it and separate it from non-magnetic impurities. After enrichment, they obtain chromite concentrate containing 46% or more chromium oxide. This is ready-made raw material for metallurgy. The concentrate is dewatered, dried, and sent to ferroalloy plants. Lump ore is needed for ferrochrome production. Fine powder doesn't melt well in the furnace. So the fine particles get agglomerated, sintered into large chunks. They mix the concentrate with fluxes and coke breeze, moisten it, and form pellets. Then they heat it to about 2,200 degrees Fahrenheit. The pellets sinter into solid lumps a couple inches across. Now the ore is ready for smelting. At the ferroalloy plant, chromite concentrate gets mixed with coke and fluxes in specific proportions. Coke is the carbon source that'll reduce the oxides down to metal. Fluxes, quartzite, dolomite, limestone, are needed to form slag with the right composition and melting point. The charge, the mix of ore, coke, and fluxes, gets loaded into the electric arc furnace from the top through special hoppers. Loading happens continuously or in batches depending on the furnace type. The electrodes, massive carbon cylinders, are submerged in the charge layer. When they switch on the current, an electric arc forms between the electrodes and the material beneath them. Temperature in the arc zone? 5,000 degrees Fahrenheit and higher. That's enough to melt any ore. Inside the furnace, complex chemical reactions take place. Carbon from the coke combines with oxygen from chromium and iron oxides, forming carbon monoxide that rises upward. Chromium and iron are reduced to their metallic state and fuse together, forming ferrochrome. Some of the carbon dissolves into the metal, producing high-carbon ferrochrome with a carbon content of 4 to 8%. Typical South African ferrochrome contains 52 to 54% chromium, 6 to 7% carbon, and 2 to 4% silicon. Ores from Zimbabwe with a higher chromium to iron ratio yield a product with 63 to 67% chromium. The molten ferrochrome and slag accumulate in the lower part of the furnace, the hearth. When enough metal has built up, they open the tap hole. Metal and slag flow into a ladle. The slag floats to the top and is poured off or skimmed away. The metal is poured into molds or cooled in special forms. Once solidified, the massive ingots are broken down by hydraulic presses or hammers into pieces of the required size. Ferrochrome production is incredibly energy intensive. A single ton of high-carbon ferrochrome burns through 2,000 to 4,000 kilowatt-hours of electricity. That's why ferrochrome plants get built in countries with cheap power, often right next to hydroelectric dams. Chromium recovery from ore hits about 90% under good conditions. The remaining 10%, it goes into slag. Slag isn't just waste. Metal particles get extracted from it using mineral processing methods, and what's left goes into construction. Ferrochrome isn't the end product. It gets shipped to steel mills where it's added to molten steel for alloying. Chromium gives steel corrosion resistance, hardness, heat resistance. Stainless steel contains 10 to 20% chromium. Average, 18%. It's chromium that forms a thin, invisible oxide film on the steel's surface, protecting the metal from rust. And so, having traveled from black rock in the Earth's depths, through quarry explosions, crushing and processing, through the inferno of an electric arc furnace at 5,000 degrees Fahrenheit, ferrochrome is born. An alloy that gives steel eternal life and shine, resistant to time and corrosion.
Imagine a river of white-hot metal as bright as the sun, born inside a giant furnace, melting everything in its path. But did you know that to create 1 ton of iron, you need almost 2 tons of rock and coal? It seems like alchemy. Hundreds of kilograms of oxygen and impurities vanish from dirty ore, leaving only pure metal behind. In the US, just a handful of these furnaces produce over 25 million tons a year, enough to build 250 aircraft carriers. And yet, there is a secret hidden within this story, one that will only be revealed to those who watch until the very end. It all begins deep in a quarry, where iron ore is mined. This isn't metal, but reddish-brown rock that looks like rusty earth. The iron is tightly bonded with oxygen, and the primary mission is to break that bond, liberating the metal within. Along with the ore, 2 other key ingredients for this infernal recipe arrive at the plant. The first is coke, a specially processed form of coal. It's baked in an oxygen-free oven to remove all impurities, resulting in pure, porous carbon that burns with incredible heat. In our process, coke is both the fuel and the main chemical agent. The third ingredient is limestone, a common rock. Its role? It's the cleaner. When heated, the limestone will act as a magnet for all the waste, collecting it into a separate mass. Now, let's go to the plant to meet the hero of our story, the blast furnace. It's a tower over 30 meters high, lined entirely with fireproof brick and wrapped in a network of pipes. This tower never sleeps. It runs continuously, 24 hours a day, sometimes for years without stopping. It is a giant stomach that must be constantly fed. From the top, using a special skip hoist that looks like a small rail car, our ingredients are charged into the furnace. Not just thrown in, but layered like an industrial lasagna. A layer of coke, then a layer of iron ore and limestone, another layer of coke, and so on. To get 1 ton of liquid iron, you need to load almost 2 tons of raw material into the furnace. This figure includes the iron ore, the coke, and the limestone. It shows just how efficiently a blast furnace works as a giant filter. It takes nearly 2 tons of rock and coal, burns away everything unnecessary, and yields 1 ton of pure, concentrated metal. This is true industrial alchemy. Once the furnace is fed, the heat is turned up. At the bottom of the furnace are special nozzles called tuyères. Through them, air is blasted in under immense pressure, superheated to 1100 degrees Celsius. This hot blast ignites the coke, causing it to burn with incredible ferocity. The entire mass of materials loaded from the top begins its long journey down through zones of increasing temperature. First, in the upper section, hot gas is rising from below dry and preheat the ore. A little further down, the chemistry begins. The burning coke reacts with oxygen to form carbon monoxide. And this carbon monoxide is our master thief. It greedily rises, meets the iron ore, and starts stripping away the oxygen atoms, leaving pure iron behind. About halfway down, the temperature becomes so intense that both the iron and the impurities begin to melt. This is where our cleaner, the limestone, comes into play. It decomposes and starts to bind with all the unwanted elements, forming a light, molten mass called slag. At the very bottom of the furnace, in its heart, known as the hearth, a lake of 2 unmixable liquids forms. At the very bottom, being heavier, lies the pure molten iron, and floating on top, like oil on water, is the lighter molten slag. Every few hours, it's time for the tapping. A special machine, like a huge drill, pierces a hole in the fireproof lining of the furnace, first for the slag. A thick, bright orange river of molten rock erupts with a hiss. Once the slag is drained, the main event begins. The drill opens another hole slightly lower down, the iron notch. And from there, with a roar and a blinding glare, a torrent of molten metal is unleashed. It isn't orange, it's a brilliant white gold, so bright it's painful to look at without special glasses. The heat radiates from it, a physical force you can feel on your skin from dozens of meters away. This dazzling river of metal, throwing off fountains of sparks, flows down a long refractory channel into a huge mobile ladle shaped like a giant cigar on wheels, known as a torpedo car. This torpedo can hold several hundred tons of liquid metal and, like a thermos flask, keeps it hot while it's transported to the next stage. What we have created in the blast furnace is called pig iron. It contains a lot of carbon, which makes it very brittle. When the metal cools in the molds, it solidifies. After the mold is broken, a finished cast iron product is revealed. And so, from a cold, red rock through the fiery stomach of the blast furnace where chemistry and heat work their magic, this heavy, reliable, and durable material is born, ready to serve us in our daily lives. Each year, blast furnaces in the United States produce roughly 30 million tons of iron. It's a number so vast, it's hard to comprehend. Let's try. The average Nimitz-class aircraft carrier weighs about 100,000 tons. This means that in 1 year, American plants produce enough iron to build a fleet of 250 of them. Or to put it in more grounded terms, if we take the weight of an average passenger car, that's enough metal to make over 12 million vehicles. An entire automotive nation born in the fire of the blast furnaces in a single year. There are only about 15 blast furnaces currently operating in the entire country. We are not talking about thousands of small plants, but a small number of true titans. This means each of these towers is an incredibly productive monster. The average blast furnace in the US produces over 5,000 tons of iron every single day. Over 90% of all pig iron produced in blast furnaces is not the final product. It is just the first step. This hot, carbon-rich metal is essentially the raw material for making steel. It is transported in torpedo cars to the next plant, where, in oxygen converters or electric furnaces, the excess carbon will be burned off, turning brittle iron into strong, ductile steel. So these 25 million tons of iron are the foundation from which skyscrapers will rise, bridges will be built, and cars, ships, and even simple tools will be made.
The metal that powers the planet. Every second, 3 electric cars are sold worldwide. Every hour, 50,000 smartphones roll off production lines, and all of them depend on one element: lithium, the white gold of the 21st century. The lightest metal on Earth, which you'll never see in its pure form because it instantly explodes on contact with water. But it's what fires up your phone, drives electric vehicles, and will power humanity's future. How do salt lakes high in the Andes transform into an energy source for billions of devices? You'll discover why lithium is called white gold, how giant evaporation pools the size of a city work, and why a real geopolitical war has erupted over this metal. Watch until the end. The finale will reveal what's behind every percentage point of your smartphone's battery. This is the story of a metal that changed the world in just 20 years.
Lithium's story began in 1817 on a tiny Swedish island called Uto. A young chemist, Johann August Arfwedson, was analyzing a rare mineral called palladium when he discovered something strange. This was a metal, but incredibly light, lighter than water. Arfwedson named it lithium from the Greek word lithos, stone. Ironic, right? A stone that floats. In 1821, British chemist William Brand first isolated pure metallic lithium through electrolysis of molten salt. What he saw blew his mind. A silvery white metal so soft you could slice it with a knife like butter, and so light that a chunk of lithium actually floats on water. But that contact with water, it lasts maybe a second. Lithium instantly explodes into a violent reaction, hissing, smoking, and it can catch fire. For 150 years, lithium was just a lab curiosity. They used it in medicine to treat mental disorders, in glass and ceramic production. But everything changed in the 90s.
In 1991, Sony released the first commercial lithium-ion battery. It was a breakthrough. Before that, batteries were heavy, short-lived, drained fast. Lithium-ion batteries turned out to be 3 times lighter and held their charge way longer. The portable electronics revolution began. Cell phones became compact, laptops became light, cameras became long-lasting. But the real explosion in demand happened in the 2010s when electric vehicles hit the market. Tesla, Nissan, BMW all built their cars on lithium-ion batteries. One electric vehicle requires 130 to 175 pounds of lithium. For comparison, a smartphone contains just 1/10 of an ounce. Demand for lithium jumped from 30,000 tons in 2010 to 550,000 tons in 2023, and that's just the beginning. Forecasts predict 3 million tons by 2030. Lithium transformed from a rare lab element into a strategic resource more important than oil.
But where do you get that much lithium? On Earth, lithium isn't rare. It's the 33rd most abundant element. But here's the thing. Concentrated deposits, not so common. There are 2 main sources, hard rock and salt brines. Hard rock means spodumene, a rare mineral mined in Australia, Canada, Zimbabwe. But the future? It's in the brines. High up in the salt lakes of South America, at 10 to 13,000 feet above sea level, lie the planet's largest lithium reserves. It's called the Lithium Triangle: Bolivia, Chile, and Argentina. Bolivia's Salar de Uyuni is the biggest salt flat on Earth. 4,000 square miles of blinding white salt under an endless sky. Looks like a massive frozen lake. Beneath that salt crust, brine, containing about 9 million tons of lithium. That's half the world's reserves. Chile's Atacama, the driest desert on the planet. Here too, massive lithium deposits hide in underground brines.
Now, let's break down how lithium is actually extracted from these salt lakes. The process looks almost magical. First, they drill wells anywhere from 65 to 330 feet deep. Powerful pumps suck up brine from these wells, a salty liquid similar to seawater, but way more concentrated. A single liter of this brine contains anywhere from 300 to 1,500 milligrams of lithium. For comparison, seawater has just 0.17 milligrams per liter. The pumped brine gets channeled into massive evaporation ponds. Picture this: artificial lakes covering dozens of hectares. From above, they look like giant colored squares: blue, turquoise, green, yellow. The color depends on mineral concentration and microorganisms. These ponds are arranged in a cascade, like giant steps. The brine flows from one pond to the next, and at each step, the magic of evaporation happens.
Under the scorching sun of the high-altitude desert and relentless winds, the water evaporates, slowly, month after month. The Atacama receives less than a millimeter of rainfall per year, but the sun shines 300 days a year, perfect conditions for evaporation. The lithium concentration in the brine gradually increases. First, unwanted salts precipitate out of the solution: sodium chloride, sulfates. They're collected and removed. The process takes 12 to 18 months. Yeah, you heard that right. Over a year just waiting for the sun to do its work. During this time, the lithium concentration grows by roughly 20 times. What started as a weak brine transforms into a thick, oily solution containing about 6% lithium. The brine turns amber yellow, almost like honey. It's pumped into specialized tanks and shipped to a chemical plant. Here begins the final stage of transforming salt water into white gold. At the plant, concentrated brine is treated with sodium carbonate, basically baking soda. A chemical reaction happens and a white precipitate crashes out of solution: lithium carbonate. It's not the metal yet, but it's a crucial compound. The precipitate gets filtered, washed, dried. What you end up with are fine white crystals, like powdered sugar. That's why lithium's called white gold. It actually is white. Lithium carbonate gets bagged up and shipped all over the world. Most of it goes to China, Japan, South Korea, wherever batteries are made. But that's not the end of the road. To make batteries, you need lithium hydroxide. Lithium carbonate gets dissolved in water, treated with calcium hydroxide. You get a solution of lithium hydroxide, which then gets evaporated. What remains are white crystals of lithium hydroxide, the final product, ready for manufacturing battery cathodes. The whole cycle, from pumping brine to getting the finished product, takes about 2 years.
There's another method for extracting lithium from hard rock deposits. In Australia and China, they mine spodumene, a mineral that contains lithium. They blast the rock, crush it, grind it into dust. Then they heat it to 1900 degrees Fahrenheit in massive rotating kilns. At that temperature, the spodumene changes its structure, becomes more reactive. The roasted rock gets mixed with sulfuric acid. A violent reaction kicks off, releasing heat and toxic gases. The lithium moves into a lithium sulfate solution. This solution gets purified of impurities, treated with sodium carbonate. Lithium carbonate precipitates out, the same product as from the brines.
But this method is way more energy intensive and expensive. You need high temperatures, massive volumes of chemicals, tons of waste gets generated. That's why the future belongs to brines. Even though right now about 60% of the world's lithium comes from hard rock, the balance is gradually shifting towards salt lakes.
Now let's look at where all this extracted lithium goes. 75% of global production goes into batteries. A lithium-ion battery is a complex device. Inside are two electrodes, a cathode made of lithium oxide with cobalt or manganese, and an anode made of graphite. Between them is an electrolyte containing lithium salts. During charging, lithium ions move from the cathode to the anode and slide between the graphite layers. During discharge, they move back, and this flow creates an electrical current. Brilliant simplicity. Lithium is ideal for this because it's the lightest metal capable of giving up electrons. A single lithium atom weighs just 7 atomic units. For comparison, lead weighs 207. That's why lithium batteries are so light and energy dense. A modern Tesla Model 3 electric vehicle contains about 24 pounds of pure lithium in its 1,060-pound battery. This battery can travel over 300 miles on a single charge. Beyond batteries, lithium is used in ceramics and glass production. It lowers melting temperatures and makes materials stronger. In metallurgy, lithium gets added to aluminum alloys, makes them lighter and tougher. In nuclear power, lithium produces tritium. In medicine, lithium carbonate is still used to treat bipolar disorder, stabilizes mood. Global lithium production in 2023 hit around 130,000 tons of pure metal equivalent. The major producers, Australia, 40%, Chile, 25%, China, 14%. Lithium prices rocketed from $5,000 per ton in 2020 to $80,000 in 2022, then crashed to $30,000. The market's volatile because demand is growing faster than supply. A real geopolitical battle has erupted over lithium. China's buying up deposits worldwide. The US is trying to build its own supply chain. Europe's hunting for alternative sources. And just like that, having journeyed from salt lakes high in the Andes through 18 months of evaporation under the merciless desert sun, through chemical plants and the most complex purification processes, lithium emerges into the world, the white gold of the 21st century, the lightest metal that powers modern civilization. This is the story of how humanity learned to turn salt water from ancient lakes into energy for billions of devices. Every time you charge your smartphone, get into an electric vehicle, or fire up your laptop, remember, inside beats a heart made of lithium, the metal for which we mine deserts and drain salt flats. The metal behind the energy revolution and the move away from oil. The metal without which the future of humanity is unimaginable. White gold extracted from snow-white salt lakes to power the planet with the energy of tomorrow. Lithium isn't just an element on the periodic table. It's the key to a future that's already here.
Every year, the world produces over 5 million tons of structural steel, and almost all of it is born from rusty scrap. Old cars, dismantled ships, demolished bridges get melted down and transformed into I-beams, the steel backbone of modern cities. From the outside, it looks simple, a piece of metal with that distinctive I-shaped profile. But this shape is the result of engineering genius, allowing a single beam to support loads of several hundred tons. A skyscraper being built somewhere in the world right now might contain a piece of armor plating from a warship, melted down and born again. This isn't just metal, it's history, sealed in steel. How does a mountain of rust become a precision structure with tolerances measured in fractions of a millimeter? And why is every modern building taller than a few stories impossible without this unassuming component. Stick around till the end. There's a moment we'll show you that's almost never seen publicly. The genius of the I-beam is in its shape. When it bends, the main load hits the top and bottom edges of the cross-section. That's where most of the steel lives, in those horizontal flanges. The thin vertical web in the middle, it just holds the flanges apart at the right distance. This gives you maximum strength with minimum weight, and that's exactly why this profile shows up everywhere you need to span a gap without wasting material. If you rolled that same volume of steel into a flat rectangle, it'd hold a fraction of the load. That I-shape isn't about aesthetics, it's math. One properly installed heavy I-beam can handle hundreds of tons. Picture a column of fully loaded semi-trucks standing on a single piece of steel. That's the real power of shape. But this story doesn't start in some gleaming factory. It starts at a massive, noisy yard that looks like a graveyard for metal dinosaurs. This is a scrap metal depot. Mountains of old cars, sliced up railroad cars, construction wreckage, and industrial junk, all waiting to be reborn. If stories about the hidden life of metal grab you like this, subscribe to the channel right now and hit that bell so every new episode lands straight in your feed. A giant crane with a powerful electromagnet descends onto this pile, and with a metallic screech, tons of old iron stick to it. This scrap is the main ingredient of the entire production process. It's loaded into a massive steel basket and sent to the melting shop, where a fiery baptism awaits. Steel is the absolute champion of recycling. The recycling rate for structural steel reaches 98%. That means practically all the metal from demolished buildings, old bridges, and scrapped ships returns to production. On average, a new I-beam is 90% recycled metal. A skyscraper being built today might contain a piece of a car from the 70s, a railroad rail from the 30s, and armor from a World War II ship. This isn't just a piece of steel, it's compressed history, remelted for new service. This is the special magic of manufacturing that almost never gets talked about. The steel cycle is virtually infinite, and each generation of cities passes its metal to the next. Every year, the US alone produces over 5 million tons of structural steel, and most of it, I-beams. That scale is hard to wrap your head around, so let's try. The steel in the Golden Gate Bridge weighs about 83,000 tons, which means American mills produce enough beams in 1 year to build more than 60 of those bridges. 60 Golden Gate bridges, every year. And that's just one country. The heart of the mill is the electric arc furnace, a giant bucket the size of a small house where scrap metal gets dumped with a deafening roar. The sight alone is incredible, tons of twisted iron crashing inside, filling the bucket to the brim. From above, 3 massive graphite electrodes descend into the furnace, each one as thick as an old-growth tree. The operator flips the switch. An electric arc flashes between the electrode tips and the metal, an artificial lightning bolt striking with colossal force. The floor fills with a deep, ear-splitting roar, and the light from the arc is so bright it blinds you even through protective glass. The temperature inside instantly rockets to 3,000 degrees Fahrenheit. The metal doesn't stand a chance. It starts melting, transforming into a boiling, blinding lake. Special additives get thrown into this molten bath: manganese, silicon, sometimes chromium or nickel, to create the exact grade of steel needed. Strong yet flexible, able to withstand massive loads without shattering like glass. The entire melting process takes 40 to 60 minutes. And in that time, tons of rusty junk completely transform into uniform liquid metal. Once the steel's ready, it needs to go from liquid river to something solid. The molten metal gets poured into a continuous casting machine. Glowing liquid flows into a special water-cooled copper mold. Passing through it, the outer layer of steel solidifies, forming a thin shell. From there, this still semi-liquid billet continuously gets pulled downward, passing through a water spray zone where hundreds of nozzles shower it with water, forcing it to solidify completely. Out of the machine crawls an endless, red-hot, massive steel billet, square or rectangular in cross-section. This is called a bloom. Automatic cutters hiss as they slice off pieces to the right length, 20, 25, 30 feet. This is our blank, the chunk of dough we're going to shape into a beam. Looks like an ordinary rectangular bar. No hint of the form it'll take in just a few minutes. These hot but now solid blooms head to the next furnace, the reheating furnace. Think of it as a giant tunnel with flames roaring inside. The blank creeps slowly through, and its temperature climbs back to the perfect working state, around 2200 degrees Fahrenheit. It becomes plastic and soft, like clay, ready for the most critical step, rolling. The quality of this heating determines just how precise and uniform the final profile will be. And now, the real spectacle begins. The bloom, heated to a blinding orange glow, rolls out of the furnace and enters the rolling mill. This is a series of gigantic steel rollers, like enormous rolling pins positioned one after another. But these rollers aren't flat. They have special grooves or calibers whose shape gradually approaches that of an I-beam. The bloom crashes into the first pair of rollers. They squeeze it with incredible force, thousands of tons, making it slightly thinner and longer. At the exit, the next rollers catch it, compressing it at a different angle and starting to form the flanges and web of the future beam. Step by step, passing through dozens of these roller pairs, the shapeless bar visibly stretches and takes on the familiar I-beam profile. A glowing chunk 20 feet long extends into a fiery ribbon stretching several hundred feet. The entire shop fills with thundering noise, the screech of metal, and the hiss of water cooling the rollers. This is one of the most powerful industrial spectacles you can witness with your own eyes. When the beam emerges from the final finishing roll, it already has perfect shape and dimensions, accurate to within 1/10 of a millimeter. Hot, long, like a fiery serpent, it travels along a roller conveyor to a massive cooling table. This giant grid is where the beam slowly cools down, releasing its heat to the air. This process can't be rushed. Cooling too quickly creates internal stresses in the metal that can later lead to deformation or microcracks, invisible from the outside. During cooling, the metal shrinks slightly, and sometimes the beam can warp just a bit. This is normal and predictable. Engineers account for this in the manufacturing process. To correct any deviation, the cooled beam is sent to a straightening machine. It runs the beam through a system of rollers that press with calculated force and squeeze out any deviation from straightness. What comes out is a perfectly straight steel profile, ready for final operations. Now we've got a perfectly straight beam, but it's not ready to ship just yet. Time for the finishing touches. First, they cut it to the exact lengths the customer ordered. Giant circular saw blades about 6.5 feet across do the job. With a deafening roar and a shower of sparks, the saw slices through thick steel in just seconds. Then, every beam goes through rigorous quality control. Inspectors check the geometry, while ultrasonic equipment peers inside the metal, making sure there are no cracks or internal defects. Only after that does the beam get its markings, basically a birth certificate with info on the steel grade, size, and batch number. Standard beams range from a few inches tall to almost 3 feet. But there are real monsters, so-called super heavy sections used in the most critical joints of skyscrapers. These beams stand over 4 feet tall and weigh up to 1,200 pounds per foot of length. Think about that. Every foot of one of these beams weighs as much as 3 grown adults. Standard lengths run 60, 80, sometimes even 120 feet. A single beam weighs as much as a battle tank. This is it. Born from rust, passed through fire and thousands of tons of pressure, it becomes the silent steel backbone of a building that'll stand for centuries. It's 1,250 feet long, 223 feet wide, and from keel to top deck, it stands 112 feet tall, like a 12-story building. This is a supertanker, the largest moving object ever built by human hands. It displaces 440,000 tons. Its holds can carry 3 million barrels of oil, enough to fill up 2 million cars. It won't fit through the Panama Canal, can't pass through Suez fully loaded, and to dock one, ports have to build dedicated offshore terminals. One of these ships cost $130 million, takes 2 years to build, and today, you're going to see how a steel giant capable of hauling an entire sea of oil across the ocean comes to life.
Everything starts with the design.
The engineering team works on blueprints for 18 months, around 50,000 separate parts, over 125 miles of welded seams. Hundreds of engineers calculate every ton of metal, every degree of hull curvature. A supertanker's hull isn't one solid structure. It's about 200 massive sections, welded individually, then assembled into a single unit. Each section weighs between 300 and 600 tons. When the design's ready, it goes to steel mills. One tanker needs 45,000 tons of specialized marine-grade steel. That's 6 times more than the Eiffel Tower. Steel arrives as sheets between half an inch and an inch thick. Each sheet runs 40 feet long, 10 feet wide, weighing up to 10 tons. Just hauling the steel takes several thousand rail cars. The finished steel storage yard at the shipyard covers 20 football fields. Tanker steel is special. It's a shipbuilding alloy with reduced carbon content and manganese additives. It withstands impact loads at low temperatures and won't crack during storms in northern seas, where water can hit 28 degrees Fahrenheit. Next up, cutting. Steel sheets enter the gas and plasma cutting shop. Plasma torches slice through metal with precision down to 0.04 inches. Arc temperature? 36,000 degrees Fahrenheit. That's 3 times hotter than the surface of the sun. A single sheet, 1 inch thick, gets cut in 2 minutes. But there are tens of thousands of sheets. The shop runs 24/7, 3 shifts, no days off. From these sheets come the future structural elements: frames, stringers, bulkheads, plating. Every part gets marked, numbered, and sent to the next stage. Then, bending. Massive rollers and presses give the steel sheets their required curves. Bow plating, rounded sides, stern contours. A 2,000-ton press bends steel like paper. Bend radius? Up to 12 inches per 3 feet of length. Now comes the most critical phase, assembling the sections. Each section is built on a separate assembly pad inside the facility. Think of them as mini factories within this massive plant. Workers lay hull plates onto the jig matrix. Steel frames, the ship's ribs, get welded on. Spacing between frames? Exactly 29.5 inches. Not more, not less. Off by half an inch, and the hull could crack in a storm. Welding is automated and semi-automated. Up to 40 welders work on a single section simultaneously. Weld depth runs 0.3 to 0.4 inches. Every seam gets checked. X-ray, ultrasound, and dye penetrant testing. One section takes 3 weeks to complete. During that time, they lay down 5 tons of weld metal. After assembly, an 800-ton gantry crane hoists the section and transfers it to the slipway. Before mounting on the slipway, each section undergoes geometric inspection. Laser systems measure it at thousands of points. If even one point deviates from the blueprint by more than 1/8 of an inch, the section goes back for rework. Because if one section's crooked, the next 20 won't fit into place. The slipway is a massive dry dock, 1,476 feet long, 295 feet wide, 49 feet deep. This is where the entire hull comes together. Assembly starts with the keel, the central longitudinal beam running the full length of the ship. It's the tanker's backbone. Everything depends on how precisely it's positioned. The keel is aligned using laser levels with accuracy down to 0.08 inches over 1,312 feet. Then the first bottom section gets mounted onto the keel. Cranes fly it in overhead. 4 riggers guide the 500-ton mass into position with inch-perfect precision. Sections are joined by welding. Each seam runs dozens of feet. Welders work inside compartments, outside on scaffolding, overhead on suspended platforms, sometimes 200 people simultaneously on a single hull. If you're fascinated by how humanity builds machines that challenge the ocean itself, subscribe to the channel. There are many more processes ahead that'll blow your mind with their scale. While the hull is being assembled, the engine room is installed simultaneously. This is the heart of the supertanker. The main engine is a diesel standing 46 feet tall, 89 feet long, weighing 2,300 tons. It's the largest reciprocating engine in the world. Each cylinder is 38 inches in diameter. The piston stroke, over 8 feet. 14 cylinders total. The engine produces 108,000 horsepower, enough to power a city of 50,000 people. It runs on heavy fuel oil and burns through 250 tons of fuel per day at full throttle. It's installed through the upper deck while it's still open. A crane lowers the engine into the engine room in sections. Then specialists assemble it on site. Assembly and calibration of a single engine take 4 months. While assembly continues, installation of the cargo tanks begins. Inside the tanker's hull, up to 15 separate compartments. Each one can store up to 25,000 tons of oil. The tank walls get coated with special epoxy paint in 3 layers. Total surface area painted, over 6.5 million square feet. If you laid out that surface, you get an area the size of 100 football fields. The paint protects the steel from corrosion. Salt, oil, and seawater, a mix that can eat through unprotected metal in a year. And a tanker needs to last 25 to 30 years. Between the tanks run pipelines. The main lines measure up to 35 inches in diameter. Total length of pipe inside the tanker, more than 25 miles. Through them, oil gets pumped in and out at rates up to 17,000 tons per hour. The tanker's cargo pumps, a separate engineering system. Each pump is driven by a steam turbine producing 2,500 kilowatts. There are usually 3 of these pumps. In a single day, they can completely unload a 1,300-foot tanker. Just 15 years ago, that would have taken 3 days. The hull is almost complete. Now they're installing the superstructure, the living quarters and captain's bridge at the aft section. The superstructure stands 92 feet tall, 8 decks. This is where 25 to 30 crew members will live and work during 3-month voyages across the oceans. They paint the hull last. Exterior paint area, 700,000 square feet. 3 coats of primer, 2 coats of top coat. Painting alone takes 2 months. Robotic sprayers work around the clock. The tanker's bottom gets a special anti-fouling paint. Without it, algae and mollusks will coat the hull in 6 months, and fuel consumption jumps by a third. This paint runs up to $20,000 per ton. Once the hull is painted, launch day arrives. They flood the dry dock. Water fills it in 6 to 8 hours, gradually lifting the 200,000-ton beast. The tanker slowly floats up. Tugboats carefully guide it out of the dock. But that's not the end. The next 4 months are spent at the dockside. They install navigation equipment, radar systems, satellite communications, anchor winches. Each winch is the size of a truck. A single anchor weighs 30 tons. Then come sea trials. The tanker heads into open water. They push her to a max speed of 16 knots. They test the steering, the engine, fire suppression systems, emergency bilge pumping. Trials last 2 weeks. Only after every check does the ship transfer to her owner. The maiden voyage of a giant like this is always an event. From the Persian Gulf to Europe, around the Cape of Good Hope, 45 days at sea. In her holds, crude oil worth $300 million. Out in the ocean, she can handle waves 65 feet high. And on the horizon, the next voyage, the next ocean, the next decades of service. Humanity has learned to build ships the size of skyscrapers that carry across the planet what powers our entire civilization. And every one of these tankers is floating proof of what engineering can achieve. Subscribe to the channel.
Every hour, somewhere in the world, a metal component weighing over 50 tons is manufactured, and a single microscopic error in its machining can trigger a multi-million-dollar catastrophe. Picture a crankshaft as long as a bus that must survive a billion cycles of explosive force, or a cylinder block where a deviation the thickness of a human hair means scrapping a multi-ton giant entirely. But here's the mystery. How do engineers achieve micron-level precision when machining parts heavier than a tank? What happens in that secret quality control room where a computer measures thousands of points and can shut down the entire process? And most importantly, stick around until the end, because I'm going to show you the final operation where one tiny slip turns months of work into scrap metal. This is manufacturing where every thousandth of an inch is a matter of engine life and death. Ready to look inside? The first thing that hits you at this facility? The sheer scale. Forget your average car engine. Take this cylinder block, for example. It can weigh dozens of tons. This isn't just a casting, it's a complex, multi-layered masterpiece of foundry art, requiring special grades of steel or cast iron that can withstand unbelievable loads, temperatures, and pressures. And here's the crankshaft. In big engines, this thing can be as long as a small bus and weigh just as much. This component is probably the most critical. It has to endure the explosive force of fuel combustion, converting it into rotational motion. The blanks often arrive as massive forgings where every pound of metal already has its own story. The process starts with incoming inspection. Specialists check the chemical composition, scan for internal defects using ultrasound and X-ray equipment. Because even the tiniest hidden flaw in a part this massive could lead to catastrophe during operation. It's like a health checkup for a steel giant. Only after a thorough inspection does the blank get clearance to enter the machine shop. Moving these blanks takes serious muscle. That's why the shop is equipped with powerful overhead cranes capable of lifting loads that outweigh most ordinary machine tools. Mounting the part onto the machining center is a precision operation requiring coordination and experience. This is the first step in turning metal into might. Now we move to the heart of the shop, the cylinder block machining zone. This is where multi-axis machining reigns supreme. Before you stands a gantry-type milling machining center. It looks more like a small house than a machine tool. Its spindles, fitted with ultra-hard cutting inserts, can remove up to several hundred pounds of metal per hour. The first operation is roughing. The goal: remove excess stock, eliminate surface casting defects, and give the part its basic geometry. The speed and sheer aggression of this cutting process? Absolutely mind-blowing. Those streams of hot chips tell you everything you need to know about the energy being dumped into this transformation. But the real magic happens later, during finishing operations. Remember when we talked about precision? For diesel engines, perfect cylinder geometry isn't just important, it's critical. That's where boring and honing come in. Boring creates the cylinder holes with micron-level accuracy. The slightest geometric error means uneven wear, compression loss, and ultimately engine failure. And honing, that's the final touch. A specialized tool with abrasive stones creates a micro-texture on the cylinder's inner surface, what we call crosshatch. This crosshatch is essential for holding oil and ensuring perfect lubrication of the piston rings. We're talking about polishing at nearly molecular level, guaranteeing engine life measured in decades. These machines operate under strict temperature control. Any temperature fluctuation can cause thermal deformation in a part weighing several tons, which means losing precision. That's why the shop floor maintains a constant microclimate, and the machining itself can run for days. Up next, meet our next hero, the crankshaft. This component works under the most demanding conditions. It needs not only colossal strength, but perfect balance. Manufacturing it, an engineering masterpiece. First up, preliminary journal machining. On specialized CNC turning milling machines, the connecting rod journals and main journals take shape. Given the weight and length of the shaft, unique support systems are used here to prevent sagging and vibration during machining. The critical stage, grinding. The shaft journals must have minimal surface roughness because that's exactly where friction with the bearings occurs. The smoother the surface, the less friction, and the longer the engine lasts. Special cylindrical grinding machines with highly sensitive sensors handle this job. Now for the critical part, heat treatment and surface hardening. After grinding, the crankshaft journals undergo induction hardening or nitriding. What does this do? It creates a super hard, wear-resistant layer on the journal surface while maintaining the core's toughness and strength. This is essential so the shaft can withstand billions of load cycles. Think of it as armor for the engine's most vital component. Final stage, balancing. Given the massive weight, even a tiny imbalance can destroy the engine. That's why every crankshaft goes through dynamic balancing. If the machine detects a deviation, counterweights are added, or material is removed from the flywheel sections until the shaft achieves perfect balance. It's like tuning a violin, except instead of music, we get harmony of rotation and power. How do you achieve that kind of precision when working with such giants? The answer lies in the tooling and quality control. The tool itself is a high-tech product. Every cutter, every mill is equipped with carbide inserts or even synthetic diamonds. They have to withstand enormous temperatures and cutting pressures. Special coatings extend the life of these tools while keeping machining quality consistently high. In a dedicated tool room, there's constant monitoring of their condition, resharpening, and replacement. But the most important thing is quality control. After every key operation, the part undergoes rigorous measurement. Coordinate measuring machines help us with this. These machines, equipped with high-precision probes and laser scanners, can measure up to 1,000 points on a part's surface with accuracy down to a few micrometers. They create a three-dimensional map of the part and compare it to the perfect computer model. If the error exceeds the tolerance, the process stops, and the part gets sent back for rework or, worst case, scrapped. No part leaves the shop floor until the computer gives the green light on its perfect accuracy. And then, when all the components, the block, crankshaft, cylinder heads, connecting rods, have passed strict inspection and achieved perfect precision, they're ready for the final stage. Assembly. This is a different shop, where sterile cleanliness reigns. Assembling an engine like this is no less precise a process than machining. All parts are thoroughly washed, removing even microscopic traces of metal chips and dirt. Specialists use torque wrenches to tighten thousands of bolts to a precisely defined spec. A mistake in torquing the cylinder head, for example, can lead to a blown gasket and engine failure. Every stage of assembly is tracked and controlled by electronic systems. Not a single bolt gets tightened without computer confirmation. After assembly, the engine heads to the test stand. Here it's fired up and gradually brought to operating conditions. Sensors measure temperature, oil pressure, vibration, power output. Any deviation from the norm, and the engine goes back for rework. Only after successfully passing all tests does the engine receive its quality certificate. These giants get installed on ocean vessels, locomotives, mining dump trucks, power plants. One of these engines can run for decades, churning out thousands of horsepower. And behind every hour of its flawless operation stand months of work by engineers, machine operators, quality inspectors. Manufacturing these engines is the pinnacle of mechanical engineering, where metallurgy, precision mechanics, and computer technology converge. And just like that, starting from a multi-ton forging, through rough and finish machining, through honing with precision down to microns, through heat treatment and balancing, through sterile assembly and rigorous testing, an engine is born, capable of running billions of cycles without a single failure. This is the story of how humanity learned to create steel hearts for the most powerful machines on the planet. Every crankshaft, every cylinder block, it's a symphony of engineering thought where an error of 1 micron means failure, and success means decades of flawless operation. When you see a massive ship crossing the ocean, or a locomotive pulling thousands of tons of cargo, remember, at its heart beats an engine, every part of which has passed through the hands of master craftsmen and the scrutiny of computers. This isn't just metal, it's the embodiment of humanity's drive for perfection, where precision is measured in microns and reliability in decades of impeccable service.
Without this metal, there'd be no electronics, no smartphone in your pocket, no computer on your desk, no satellite in orbit. Every second, millions of microchips are being soldered worldwide, and they all depend on tin. The metal that 5,000 years ago launched humanity into the Bronze Age today connects transistors and processors. The oldest metal of civilization became the foundation of the digital revolution. How do gray rocks from the jungles of Malaysia become the silvery metal that flows from your soldering iron? You'll learn why tin doesn't rust, how it changed the course of human history, and why modern industry would collapse without it. Watch until the end. The finale reveals what's behind every microchip in your phone. This is the story of a metal that survived millennia and remained irreplaceable. Tin's story predates writing itself. Around 5,000 years ago, in the 3rd millennium BC, someone accidentally mixed copper with tin. The result? An alloy harder and stronger than both metals, bronze. It changed everything. The Bronze Age began, an entire civilizational era named after a tin alloy. Bronze swords, axes, armor were sharper and lasted longer than stone and copper. Armies with bronze weapons conquered continents. There was one problem. Tin was rare. Copper could be mined everywhere, but tin only in a few places on Earth. Cornwall in Britain, Bohemia in Central Europe, the mountains of Afghanistan. Expeditions traveled thousands of miles for tin. Phoenician traders sailed to Britain's foggy shores across the entire Mediterranean just for tin. The metal was valued more than gold. Whoever controlled tin deposits controlled military power. Civilizations rose and fell depending on access to this silvery metal. In the Middle Ages, tin was used to make tableware. Tin cups, plates, mugs. Tin doesn't rust and doesn't give food a metallic taste. Rich people ate from tin, poor people from wood or clay. Tin soldiers became a favorite toy for children in the 19th century. They were cast by the millions. But a strange danger lurked. At temperatures below -13 degrees Celsius, with tin, something miraculous happens. The silvery metal starts turning into gray powder. This is called tin pest. The crystalline structure reorganizes, the metal crumbles. During cold winters, tin buttons on soldiers' uniforms turn to dust. Tin pipes and church organs inside unheated cathedrals disintegrated. Napoleon lost his army in Russia, not just from the cold. Tin buttons on soldiers' uniforms crumbled, clothing fell apart. Tin past played its role in history. Modern tin is treated with additives that prevent this transformation. But pure tin in freezing temperatures still turns to powder. Where does tin come from today? Tin is a rare element. It makes up just 0.02% of Earth's crust. The primary tin mineral is cassiterite, tin oxide, dark brown or black crystals, incredibly heavy, density almost 7 grams per cubic centimeter, heavier than iron. The largest deposits are in Southeast Asia, Indonesia, Myanmar, Thailand, Malaysia. They account for about 70% of global production. There are deposits in China, Peru, Bolivia, Australia. Tin is extracted 2 ways: open pit mining in quarries or washing from placer deposits. Placers form when cassiterite gets weathered out of rock by rivers over centuries and accumulates in valleys. Heavy crystals settle to the bottom. Lighter rock gets carried away by the current. In Malaysia and Indonesia, entire islands are made of tin-bearing sands. That's where most of the world's tin comes from. Then begins the dramatic process of transforming dark stone into silvery metal. Tin mining from placer deposits uses giant dredges. Picture a floating factory, a steel ship with a massive pipe that descends to the bottom. At the end of the pipe, a cutter head with teeth rotates. It tears into the bottom sand, grinds it up. Powerful pumps suck up the mixture of sand and water, slurry, and lift it to the surface. The ship has washing equipment installed, a system of flumes, screens, and centrifuges. The slurry flows down inclined flumes lined with special mats. Light sand washes away with water, while heavy cassiterite crystals get trapped in the mat fibers. It's like gold mining, except instead of gold, it's tin. Periodically, the mats are removed and shaken out. You get a concentrate, dark sand containing up to 70% cassiterite. The rest is impurities from other minerals. This concentrate is re-washed on special tables, blown with air to separate light particles. The final concentrate contains about 75% tin oxide. It's dried and shipped to the smelting plant. At the plant, cassiterite is reduced to metallic tin. The concentrate is mixed with coke, carbon, and loaded into a reverberatory furnace. It's a massive furnace, the length of a bus, lined with refractory brick. Inside, temperatures reach 2,400 degrees Fahrenheit. Natural gas or fuel oil burns, flames reflect off the furnace roof and heat the mixture from below. At this temperature, carbon strips oxygen from the tin oxide. Cassiterite is reduced to metal. Molten tin collects at the bottom of the furnace, a silvery pool glowing orange from the heat. Tin's melting point is just 450 degrees, one of the most easily melted metals. The molten metal is periodically tapped through a tap hole, an opening in the furnace's sidewall. Silvery metal flows into ladles, but this isn't pure tin yet. It contains impurities: iron, copper, lead, arsenic. Refining is needed, purification. The molten tin is heated to 750 degrees and blown with compressed air. Impurities oxidize and float to the surface, a slag. The slag is skimmed off, the blowing repeated, several times over. Pure tin gets poured into molds, creating ingots weighing about 66 pounds each. Silvery white, shiny. Tin is incredibly soft. You can scratch it with your fingernail. But it has this amazing property. It doesn't oxidize in air. More precisely, it forms this ultra-thin oxide film that protects the metal from further corrosion. That's why tin cookware lasted for centuries. Today, most tin doesn't go into cookware, it goes into electronics. 70% of global tin production is used for soldering. Solder is an alloy of tin with lead or silver. The melting point of solder is around 400 degrees Fahrenheit, low enough that it won't damage electronic components. When you're soldering a microchip to a circuit board, the solder melts, flows into the gaps, cools down, and forms a solid electrically conductive connection. Without tin, assembling electronics would be impossible. Every smartphone contains thousands of soldered connections. Every computer motherboard, tens of thousands, all held together by tin. Tin is also used for tinning, coating other metals with a thin layer of tin. Tin cans, they're actually steel, just coated with tin inside and out. A layer of tin just a few microns thick protects the steel from rust and prevents food from contacting iron. Making tin plate, that's the second largest use of tin. Tin alloys are used in bearings, Babbitt metals, alloys of tin with copper and antimony. They're soft, lubricate well, handle heavy loads. Organotin compounds serve as stabilizers in PVC plastic production. Global tin production runs around 350,000 tons per year. That's tiny compared to steel or aluminum. But tin, it's a strategic metal. Without it, the electronics industry grinds to a halt. Tin prices hover around $25,000 per ton, 10 times more expensive than aluminum. Tin reserves are limited. Accessible deposits will last maybe 30 years at current extraction rates. That's why tin gets actively recycled, recovered from electronic scrap during disposal. Here's something interesting. Tin is one of the few metals we actively recycle. Electronic waste recycling has become an entire industry. Old circuit boards from computers, smartphones, and TVs get collected and shipped to specialized facilities. There, the boards are shredded, treated with chemicals, or heated. The tin dissolves or melts out, then gets extracted and purified. From 1 ton of electronic waste, you can recover up to 22 pounds of tin. This is economically and environmentally profitable. First, it reduces the strain on natural deposits, which aren't that abundant anymore. Second, you don't need to spend energy on mining and processing ore. Tin recycling requires 10 times less energy than primary production. In developed countries, up to 30% of tin comes from recycled materials. Japan, which has no deposits of its own, recycles up to 50%. And just like that, traveling from dark cassiterite crystals in tropical placer deposits, through the hellish heat of furnaces at 1300 degrees and countless purification stages, tin emerges into the world. civilization's most ancient metal, now the backbone of modern electronics. A metal that 5,000 years ago gave humanity bronze and empires, and today connects billions of transistors and processors. This is the story of how a rare element survived millennia without losing its value. What's more, it became even more critical. Every time you power up your smartphone, computer, or any electronic device, remember, inside, thousands of tiny droplets of tin hold microchips together. Without this soft silvery metal, there'd be no internet, no satellites in space, no artificial intelligence. Tin, the silent hero of the technological revolution, the metal that bridges past and future. From bronze swords of antiquity to microprocessors of today. 5,000 years of service to humanity. And this isn't the end. It's the continuation of a metal story that never goes out of style.
You believe that in the United States alone, the electrical wire industry pulls in tens of billions of dollars in revenue every single year? These seemingly small spools of wire carry the entire flow of energy that keeps modern civilization running. Behind every foot of wire lies rigorous engineering. Copper is drawn through a series of steel dies to hit precise dimensions, then coated with layers of insulation designed to withstand heat and resist moisture. A deviation of just a few thousandths of an inch can lead to overheating, short circuits, and serious safety hazards. In this documentary, we're going inside the manufacturing process of electrical wire, the invisible foundation of modern life. From a thin strand of metal that seems almost fragile, electrical wire becomes the silent foundation of modern life. At a diameter of just about 0.08 inches, a single copper conductor can carry enough current to light up an entire house. Inside its thin insulation layer flows a constant stream of energy, transforming invisible motion into light, heat, and the continuous operation of the world around us. And when its mission is complete, electrical wire doesn't reach the end of its life. Copper can be reborn almost infinitely. The plastic insulation is stripped away, the metal is cleaned, melted down, and drawn again into new wire. Each recycling cycle consumes far less energy than mining and refining new ore, reducing waste and preserving natural resources. It's a closed loop, where technology and sustainability coexist in something as small and unassuming as a single wire. The journey of an electrical wire begins deep underground, in massive copper mines, where the red metal is extracted from ancient layers of rock. Copper ore doesn't exist in pure form. It's locked tight inside stone, soil, and mineral compounds. To reach it, people must drill, blast, and remove layer after layer of geology, hauling thousands of tons of rock to the surface every single day to recover just a tiny amount of copper. On average, producing a single pound of refined copper requires processing anywhere from 200 to 1,000 pounds of raw ore, depending on the metal content in each deposit. This shows that copper's value comes not from abundance, but from the precision required to extract it from an enormous mass of material. Most modern copper mines are giant, open-pit operations, hundreds of feet deep and miles wide. Seen from above, they look like colossal funnels carved into the Earth's surface. Every day, hundreds of ultra-heavy dump trucks, each hauling over 300 tons of rock, move continuously between the pit and the processing facilities. Once ore leaves the mine, it's still nothing more than solid rock with metal locked inside. To reach the copper, the first critical step is primary crushing, breaking down the rock's structure and freeing up the mineral particles. At the crushing plant, ore gets reduced through multiple stages, from large rocks to gravel and finally into a fine powder. The finer it becomes, the more efficiently copper-bearing minerals separate from the surrounding waste rock, preparing the material for the next stage of separation and concentration. Then the powdered ore goes into the flotation process. Water, air, and very small amounts of chemicals combine to create countless microscopic bubbles. Copper-bearing mineral particles attach to these bubbles and rise to the surface, while the heavier, worthless rock sinks to the bottom. This is the first true separation step, where the metal begins to be recognized and isolated from the rest of nature. The result is copper concentrate, containing 25 to 35% copper, a dramatic increase from the initial 1 to 5% found in raw ore. Though this isn't pure copper yet, this concentration stage is crucial. It transforms mountains of seemingly worthless rock into a metal resource with real industrial value. After crushing and flotation, the concentrate still isn't metal. At this stage, copper remains locked inside mineral compounds and requires one decisive step to be fully liberated: smelting. The concentrate is fed into furnaces operating at extremely high temperatures, often exceeding 2,300 degrees Fahrenheit. Under this intense heat, sulfur compounds and impurities begin to break down. They burn off, vaporize, or separate into slag, while the heavier metal settles at the bottom. This is the moment when mineral ore truly transforms into metal. After smelting, the resulting copper is known as blister copper, with a purity of 98 to 99%. Its surface shows a characteristic dark red color. The metal is dense, heavy, and conducts electricity far better than any mineral form before it. From rock and powdered ore, copper emerges for the first time as an industrial metal. Once copper is in its molten metallic state, it must be shaped into a form that can be transported and further processed. Here begins the casting stage. A stream of liquid copper, glowing red like lava, is drawn from the furnace and poured into heat-resistant steel molds where the metal's shape is first controlled with precision. Within minutes, the temperature drops and the copper solidifies into dense metal blocks known as billets or ingots. After casting into rough copper plates, the metal is still not pure enough to serve as an electrical conductor. Tiny impurities remain inside, small enough to escape the eye but significant enough to reduce transmission efficiency. To meet electrical industry standards, copper must go through an almost absolute purification step: electrolytic refining. Rough copper plates are suspended in large tanks filled with electrolytic solution. When electrical current flows, the metal surface slowly dissolves. Each copper atom separates from the rough plate and moves through the solution. On the opposite side, these atoms settle on cathode plates, forming a new layer of copper that is brighter, purer, and more uniform in structure. The result is copper sheets with purity up to 99.9%, the level required for electrical power systems. After refining, high-purity copper is remelted and cast into large round rods called wire rod. These rods are about half an inch in diameter and serve as the starting point for all subsequent wire drawing processes. Wire drawing is the process of gradually pulling metal through a series of progressively narrower steel dies, each one slightly smaller than the last. When the copper rod is pulled through the first die, its diameter decreases slightly while its length increases. The process repeats through the second, third, and each subsequent die until the wire reaches the required thickness. Throughout this process, the wire is coated with a special lubricating solution to reduce friction, limit heat buildup, and protect the metal surface. Wire drawing doesn't happen in one step. It's a sequence of gradual reductions. A single wire typically passes through 10 to 30 different dies before reaching its final size. For example, from an initial diameter of about half an inch, the wire can be drawn down to around 0.08 inches, and even much smaller for electronic wires. As the copper is continuously stretched, its internal crystalline structure becomes harder and loses its natural ductility. For this reason, after a certain number of drawing passes, The wire must be lightly annealed at temperatures from 600 to 800 degrees Fahrenheit to soften the metal again. After the wire is drawn to the right size, the individual copper strands are still too thin and too stiff to be used on their own. To become the flexible, durable conducting core in real-world applications, they have to go through a twisting process. Copper strands are fed into a twisting machine, where dozens of spinning spools work simultaneously, twisting each strand around a central axis at a precisely calculated angle. This twist angle directly determines the flexibility and bend strength of the wire. A tighter twist creates a stronger, more compact core. A looser twist makes the wire more flexible. That's why every type of electrical cable, from household wiring to industrial power lines, has its own specific twist structure. A single conductor can be made from 7, 19, 37 strands, or even more. These numbers aren't chosen randomly. They follow geometric patterns that allow the small wires to fit tightly together, forming a round, uniform core with minimal empty space and even distribution of electrical current across the entire cross-section. Thanks to the twisted structure, mechanical stress is distributed among many small wires, significantly reducing the risk of cracking or metal fatigue. At the same time, microscopic gaps between the strands help dissipate heat more efficiently as electrical current passes through the conductor. Once the copper core has been fully twisted, it still can't be used safely. Bare metal conducts electricity too powerfully. Even the slightest point of contact can cause short circuits or pose serious danger to people. That's why the conductor must move to the insulation stage. The twisted core runs continuously through an extrusion system, where insulating materials like PVC, PE, or cross-linked polyethylene are melted and pressed tightly around the entire metal surface. The molten plastic flows evenly in tubular form, wrapping tightly around the copper core and forming a completely sealed layer. This becomes the protective sheath that prevents electricity from leaking and isolates the conductor from the environment. The thickness of this insulation layer is controlled with extreme precision. If it's too thin, safety is compromised. If it's too thick, the cable becomes stiff, difficult to install, and wasteful of material. For this reason, diameter sensors work continuously during extrusion, ensuring the plastic coating remains uniform along the entire length of the wire. Immediately after coating, the cable passes through a cooling system using water or air, allowing the plastic to harden quickly and hold its precise shape. Once the insulation layer has completely cooled and stabilized, the wire feeds directly into the winding machine. Before reaching the spool, it passes through a tension control system that keeps the cable in a perfectly balanced state. It can't be too loose, which could cause tangling, and it can't be too tight, which could stretch the copper core or deform the plastic insulation. The spool rotates smoothly while a lateral guide mechanism moves back and forth, laying the wire in parallel, tightly aligned loops. Each turn is placed neatly beside the previous one, building layer by layer into a uniform, perfectly formed coil. Throughout the winding process, wire length is continuously measured by sensors. When the preset number of feet is reached, the system automatically stops, cuts the wire, and secures the end of the spool. After winding, the wire moves to the packaging area for protection against dust, moisture, and physical damage. Each spool is wrapped in plastic film or shrink wrap, and larger spools are additionally secured with plastic straps or steel bands to maintain their shape. Next, technical information such as wire type, cross-section, length, voltage rating, and production date is clearly marked on the packaging. From deep copper mines beneath the Earth's surface, the red metal embarks on a long journey through science and industry to become electrical wire. Every single stage, from refining and forming to drawing, twisting, insulating, spooling, and packaging, demands extraordinarily high technical precision. What appears to be a simple product is actually the result of ancient geology, modern engineering, and a massive manufacturing system operating without pause. If you're fascinated by the hidden stories behind everyday objects, where industry and science unite to shape the world we live in, subscribe to the channel. Every video is a journey into how humanity transforms raw resources into the foundations of modern civilization.
Have you ever seen what molten bronze looks like? I have. It's golden, almost like the sun, and flows slower than water, thick, heavy, with this inner weightiness to it. And when 70 tons of this metal get poured into a single mold all at once, it's a sight you can't look away from. Today we're at a factory that makes propellers for military ships. This is one of those places they don't run tours through and almost never film inside. And I'm going to show you the entire journey from molten bronze to a polished giant that will silently push thousands of tons of steel through the ocean. Let's start with a question I asked myself when I got here. Why bronze? A warship is a steel machine. Steel hull, steel superstructure, steel weapons. So why make the propeller from a different material? The answer is simple yet profound. Steel rusts in seawater. The propeller is constantly submerged, constantly spinning, constantly in contact with an aggressive environment. A steel propeller would turn into a rusty hedgehog in just a few years, one that can't do its job anymore. That's why they use nickel aluminum bronze here, an alloy that sailors and metallurgists call nibral for short. Nibral is a mix of copper, aluminum, nickel, and iron in precisely calibrated proportions. Copper provides the base and corrosion resistance. Aluminum strengthens the alloy and reduces weight. Nickel adds hardness and erosion resistance, and iron refines the grain structure, making the metal uniform. Every element here is deliberate, the result of decades of research and real-world testing. Nibral doesn't rust, resists erosion incredibly well, and has enough strength to handle the loads from spinning at full speed underwater. Now, about scale. A propeller for a destroyer or nuclear submarine, this isn't something you can pick up with your hands. The diameter of such a propeller reaches 20 feet or more, and each blade is comparable in size to a small car. The weight of the finished product, dozens of tons. And it all starts with 70 tons of liquid bronze that needs to be poured into a single mold in one continuous process. 70 tons. That's roughly the weight of 12 fully loaded pickup trucks. And all this massive metal at a temperature of around 2,000 degrees Fahrenheit has to get into the mold evenly, no pauses, no stops. The metal is melted in large induction or arc furnaces. Depending on the plant's configuration, there might be several of these furnaces, and they run in parallel to accumulate the necessary volume of molten metal by the time of pouring. When the metal hits the right temperature, lab techs take a sample, a small portion of the melt, and send it for rapid chemical analysis. If the element ratios check out, they greenlight the pour. If something's off, they adjust it right there in the furnace, adding whatever element is needed, then take another sample. The pour happens from a big ladle suspended from an overhead crane. They tilt the ladle, and metal starts flowing into the gating system of the mold. It looks like this, a thick golden stream with bright glow and a cloud of steam rising up. The air shimmers from the heat, and 30 feet away you can feel the hot wave hit your face. The foundry workers stand off to the side in protective suits and shields. Even several yards out, the heat hits your whole body. They control pour temperature by adjusting the ladle tilt. Too fast and the metal churns turbulently in the mold, trapping air and creating voids. Too slow and the first portion starts solidifying before the mold fills, leaving internal seams in the casting. So the pace stays steady, continuous, dialed in by experience. When the mold is complete, they leave what's called a riser at the top, an extra reservoir of metal that feeds the casting as it shrinks during cooling. Without it, shrinkage cavities form inside the propeller, voids that would render the blade useless. The riser gets cut off later, but during the pour, it's a critical part of the process. The mold for a propeller is a massive structure that takes up a significant portion of the foundry floor. It's assembled over weeks from special molding sand reinforced with binding resins. Each blade has its own complex geometry, twisted, uneven, with a precisely calculated profile. This geometry is built into the sand mold with high precision. The raw casting already needs to be very close to the final part. Worth noting separately are the cores. Cavities are designed inside the blades to reduce weight without sacrificing strength. To form them, sand cores are mounted in the mold on metal supports called chaplets. During the pour, the chaplets fuse with the base metal and become part of it, while the cores are later knocked out of the finished casting. Sounds simple, but in practice, it's precision work, carefully controlling the position of every rod. If a rod shifts under the weight of molten metal during the pour, the blade wall comes out uneven. An uneven wall means imbalance. Imbalance on a submarine propeller means vibration. Vibration means noise. And noise underwater? That's a death sentence for a sub, because enemy hydrophones will pick it up. This brings us to the main theme of this facility: silence. A warship, and especially a submarine, must be as quiet as possible. The propeller is the primary source of underwater noise. There are two mechanisms: mechanical noise from imbalance and vibration, and cavitation noise. Cavitation is a phenomenon where microscopic vapor bubbles form on the blade surface due to pressure differences, then collapse with a distinctive crackle. Each pop is a micro-impact that, over time, destroys even bronze, leaving small pits on the surface. But the main problem isn't wear, it's sound. That crackling travels brilliantly through water and is easily detected by sonar systems. That's why blade surfaces must be perfect: no roughness, no waviness, no deviations from the calculated profile. That's exactly why there's a 5-axis CNC milling machine standing here. If you've never seen one of these machines, picture something between an industrial robot and a building. The work envelope can handle parts up to 20 feet in diameter. The spindle and cutter move simultaneously along 5 axes, 3 linear and 2 rotational. This lets the tool approach any point on a complexly twisted blade at exactly the right angle and remove metal with micron-level precision. The price tag on one of these machines? A small fortune. But without it, achieving the required surface quality on parts this size is simply impossible. Machining a single propeller takes several weeks. Weeks, not hours. The machine strips away chips continuously, layer by layer, closing in on the final profile. Bronze shavings curl into golden spirals and drop into the catch pan, while beneath the cutter emerges a surface smooth as glass. Operators regularly pause the process to measure blade geometry using specialized probes and laser scanners. Any deviation from the theoretical profile? The program gets adjusted. The goal is to achieve a surface that matches the blueprint to within hundredths of a millimeter on a part that's 20 feet across. That's like drawing a perfect room-size circle without deviating from the line by more than the thickness of a sheet of paper. After machining comes balancing. The propeller gets mounted on a balancing stand and spun. Sensors detect exactly where the imbalance is and how much. Technicians manually remove metal from specific spots, literally just a few grams at a time, until the propeller reaches the required balance level. The process is painstaking. Shave off a tiny bit, measure. Shave again, measure again. Over and over until the sensors show it's within spec. On a civilian ship, this level of precision would be considered excellent. On a military vessel, it's the minimum acceptable standard. The final inspection includes complete measurement of every blade, surface roughness checks, and verification of the metal's chemical composition using samples taken during the melt. Each propeller gets a full documentation package, from the melt's chemical analysis to balancing protocols and laser surface scanning reports. This isn't just paperwork. It's a legal and technical passport for a product that'll go on a warship and serve for decades under the harshest operating conditions. I stood next to a finished propeller before shipping, trying to wrap my head around the fact that I was looking at something that had gone from liquid bronze to this golden, polished giant in just a few months, through the work of dozens of people and one very large machine. Somewhere out in the ocean, this propeller will spin in complete darkness, pushing thousands of tons of steel forward. And it'll do it silently. Because that's exactly what it was built to do.
Every year, aircraft around the world cover more than 25 billion miles. That's roughly 26,000 trips around the Earth. And it's all thanks to the heart of aviation, the turbofan engine. Inside, there's a genuine inferno where temperatures reach over 1,100 degrees Celsius. But how can a machine made of metal survive where steel melts? How do they craft blades with micron-level precision that spin faster than a bullet? And why are some components today literally grown from powder using lasers? Stay with me till the end, and you'll discover a secret that'll forever change how you think about engineering. Turbofan engines that power the giants of the sky, Boeing and Airbus aircraft, seem like something out of science fiction. Yet they're the genuine embodiment of engineering brilliance. How do you assemble these remarkable machines from tens of thousands of parts and materials like pieces of a puzzle? Ordinary metals simply won't do for their manufacture. The engine must operate in conditions where temperatures can exceed 1,100 degrees Celsius. It's a proper inferno, and ordinary steel simply wouldn't cope. This is where titanium alloys enter the picture. Lightweight, robust, and capable of resisting melting in extreme heat. And for the hottest zones of the engine, they use nickel-based superalloys. Such extreme temperatures arise from the fuel combustion process in the combustion chamber. During engine operation, aviation fuel, typically kerosene, mixes with air and ignites, creating hot gases. These gases literally accelerate to extraordinary speeds and temperatures, over 1,100 degrees Celsius, sometimes reaching 1,500 in modern engines. This level of heat is essential to achieve maximum efficient thrust. That is, the hotter and faster the gases, the stronger the energy flow that drives the turbine and propels the aircraft. Here lies the principal challenge. The engine must not only withstand these extreme conditions, but also operate reliably. You know what's remarkable about the engine manufacturing process? Even individual components, such as turbine blades, are crafted with micron-level precision. For instance, blades are cast in a vacuum to ensure there isn't even the slightest crack inside. Some are formed to have a single crystal structure, meaning the metal has not a single seam. But that's not all. Three-dimensional printing? Yes, that's used too. For instance, for complex components that are impossible to create through traditional casting. Turbine blades are the engine's heart. They operate in the hottest zone and convert the energy from hot gases into rotational movement. First, a blade model is created from wax. Then the show begins. In a special furnace, superalloys are melted, composed of nickel, chromium, and other metals capable of withstanding temperatures above 1,100 degrees. This molten metal is poured into a ceramic mold. But the secret lies not only in the material, but also in how it's done. To ensure the blade withstands tremendous temperatures and stresses, it's often cast as a single crystal. This means the entire piece of metal has no seams or micro cracks. Why does this matter? Seams or micro cracks in such conditions are like a minefield. One error and the blade fails. Single crystals are grown through very gradual cooling. Once the metal cools, the ceramic mold is broken away and the blade undergoes thorough grinding. A special heat-resistant coating may be applied to the surface. And so, each blade is inspected individually. If there's even the slightest defect, it doesn't proceed further. Fuel injectors, combustion chamber components, or even compressor blades in aviation are manufactured using three-dimensional printing. For instance, GE Aviation prints injectors for their engines that weigh 25% less but are 5 times stronger than traditional ones. Layer by layer, from powder and light, components are created that allow aircraft to fly faster, further, and more efficiently. First, engineers create a digital three-dimensional model of the component with maximum precision. Here, every curved surface or cavity matters. Why? Because these components often operate in places where a millimeter can change everything, from engine efficiency to its reliability. Instead of the usual chunk of metal, they use ultrafine powder here, for instance from titanium, nickel, or Inconel. It resembles sand, but with particles so minute they're barely visible to the naked eye. The powder is poured into a special reservoir and it becomes the building material. The printer's working principle is straightforward yet brilliant. It melts the powder using a laser or electron beam. The laser heats the powder to such a temperature that it literally fuses into a uniform metallic structure. Then the next layer of powder is applied and the process repeats. This method is called selective laser sintering or melting. And here's what's splendid. Three-dimensional printing allows the creation of even the most complex geometrical forms. For instance, components with internal cooling channels that simply cannot be manufactured through casting or milling. You see, in traditional manufacturing, you often need to create a large component first, then cut away everything superfluous. The resulting component isn't quite ready yet. After printing, it undergoes heat treatment, heated and gradually cooled to relieve internal stresses in the metal. Then comes final grinding, polishing, or mechanical processing if precision needs correcting. And naturally, each component passes rigorous testing. After all, this is serious business. If a component can't bear the load, the consequences could be catastrophic. Engine assembly takes place in an enormous hangar, where every square foot is occupied by tools, engine parts, and people in overalls. Everything begins with the engine casing, resembling a gigantic metal cylinder. This is the skeleton to which all other parts will be attached. The casing is crafted from titanium or nickel alloys, as it must withstand tremendous loads. Engineers work like watchmakers. The casing is secured in an enormous machine to ensure everything is absolutely straight. Next come the compressors, several rows of blades responsible for compressing air before feeding it into the combustion chamber. Blades are installed one after another. Each is inspected manually. Following the compressors comes the turbine stern. Next, the combustion chamber is installed, the engine's genuine inferno. Here, compressed air mixes with fuel and burns. Engineers install special injectors that ensure uniform fuel delivery. And here, everything must be perfect. An incorrect injector angle, and the engine could lose efficiency or even fail. Running through the entire engine is a central shaft, a sort of backbone. At one end of the shaft, the fan is mounted in the form of an enormous wheel at the engine's front, whilst at the other end sits the turbine. To install the shaft, they employ special robots. Once the engine's internal section is assembled, external systems are added. Fuel pipes delivering combustion to the combustion chamber. The oil system ensuring lubrication of all moving parts. And electronics, because the engine is literally packed with sensors monitoring temperature, pressure, revolutions, and much more. These elements are secured using cables, tubes, and bolts that must withstand not only vibration, but also extreme temperatures. After assembly is completed, the engine isn't dispatched to an aircraft straight away. First, it's mounted to a test stand where real flight conditions are simulated. Once the engine passes all tests, it's disassembled, the principal components are inspected once more, and then it's assembled definitively. The finished engine is packaged and transported to a Boeing or Airbus factory where it becomes part of a new aircraft. So there you have it. Component by component, engineers create the aircraft's heart, capable of carrying thousands of passengers across continents. Isn't that a modern masterpiece? Do write and let me know if you'd like to see more videos like this.
Every year, the world produces over 20 million tons of mineral wool, with nearly half of that volume coming from the United States. This is a material capable of withstanding direct flame contact at temperatures of 1,500 degrees Celsius, whilst weighing less than the air trapped inside it. How does solid, heavy volcanic rock, born in the Earth's fire, become a light and fluffy insulator resembling delicate candy floss? How have engineers harnessed fire powerful enough to melt stone to create silence and warmth in our homes? And most importantly, what secret do these enormous factories hide as they transform tons of dirty industrial waste into a clean and safe product for the future? Watch until the end, because what follows is a fact that will forever change your perception of this remarkable stone fleece.
The mineral wool market in the United States is a colossal, invisible machine, churning billions of pounds. We're talking about an industry worth over 4 billion pounds per year. And according to analysts' forecasts, it's only set to grow. This means that right across the country, from the frozen forests of Minnesota to the scorching deserts of Arizona, more and more builders and homeowners are choosing this rock-based jumper for their walls, roofs, and floors. But the story of this material doesn't begin in a factory. It starts deep within the Earth's crust, in the thunderous heart of a quarry. The foundation of it all is basalt. This is a dark, dense volcanic rock, the very material that forms the ocean floor, and which millions of years ago erupted from volcanic vents. But alongside it comes a rather unexpected partner: slag. This is a byproduct from metallurgical giants, a solidified melt of impurities left behind after steel smelting. Once considered worthless waste and simply carted off to landfills, creating entire man-made mountains, today it's invaluable raw material.
Right then, picture the recipe for this industrial marvel. Take several portions of prime crushed basalt for strength, add a touch of slag to achieve the desired chemical properties, and for eco-friendliness and energy savings, generously season it all with recycled glass and offcuts of old mineral wool. All these stony ingredients arrive at the factory in enormous lorries and get tipped into a giant hopper. And now the real inferno begins, quite literally. From the hopper, this mixture, called the charge, flows continuously into an enormous vertical tower, a cupola furnace, or what's known as a cupola. It's a genuine miniature volcano created by human hands. Here, Rather like feeding an insatiable maw, they load our stone mixture in layers, along with coke, a special fuel derived from coal that burns with incredibly high and stable heat. Massive fans, roaring like aircraft turbines, pump thousands of cubic meters of air into the furnace, driving the temperature up to absolutely astronomical levels, 1,500 degrees Celsius.
At such temperatures, the stone hasn't got a chance. It melts, cracks, and transforms into a liquid mass glowing an incandescent white. This river of fire flows out of the furnace along a special channel lined with fire brick. The sight is absolutely mesmerizing. A brilliant, blinding stream of molten stone radiating such intense heat that one simply cannot stand nearby without proper protection. And here, at the exit from this inferno, a genuine miracle occurs. The transformation of heavy, viscous liquid into light, airy fluff. This process is called fiber formation. Have you ever watched candy floss being made? A spinning center where sugar is poured in, and fine threads that fly outwards. The principle here is exactly the same, but instead of sugar, molten stone, and instead of a small machine, a gigantic centrifuge. A thin stream of this stone lava hits several massive disks spinning at tremendous speed, making thousands of revolutions per minute.
When a droplet of molten rock strikes such a disk, the colossal centrifugal force instantly stretches it and flings it aside as an incredibly fine fiber, just a few microns thick. That's 10 times thinner than a human hair. Since this process occurs continuously, an entire cloud of red-hot stone threads flies off the disks. It resembles a golden, luminous chaos. Billions of these finest fibers, cooling as they fly, transform into a light, wool-like mass. In just a moment, our heavy molten rock has become airy and fluffy. But for now, it's simply a formless cloud that needs to be gathered together. Whilst the fibers are still airborne inside a special chamber, a fine mist of binding agent is sprayed onto them from hundreds of nozzles. This is a special phenol formaldehyde resin that envelops each tiny fiber.
This cloud of glue-soaked fibers flies onwards and enters the settling chamber. At the bottom of this chamber sits a wide moving conveyor with a perforated belt. From beneath the belt, powerful fans extract air, creating a vacuum. This directed airflow pulls the fibers downward and lays them evenly onto the conveyor, forming a thick, fluffy carpet. This already resembles the future insulation, but it's still soft and the glue hasn't hardened yet. The thickness of this carpet is controlled by the conveyor's speed. The slower it moves, the thicker the layer that settles. And now this golden yellow fluffy carpet, reminiscent of a giant Swiss roll, is ready for the final stage, baking. It slowly enters an enormous oven known as a curing chamber. This is a long, multi-level tunnel maintained at a temperature of around 200 degrees Celsius. The purpose of this stage isn't merely to dry the carpet, but to bake the adhesive. Under heat, the resin polymerizes. That is, its molecules cross-link into a robust three-dimensional network, transforming into solid plastic that permanently bonds the stone fibers at their intersection points. It's within this oven that mineral wool acquires its final properties. It becomes resilient, capable of recovering its shape after compression. During this process, the resin often changes color, lending the finished product its characteristic yellowish-brown hue. From the other end of this gigantic toaster oven emerges no longer a loose carpet, but rather a solid, springy mat of specified thickness and density.
However, it still remains an endless ribbon. Now it's time to transform it into a marketable product. This hot mat passes through an entire system of cutting tools. Sharp circular saws or powerful blades slice it lengthways and crossways with incredible precision into sheets or rolls of standard dimensions, for instance 16 or 24 inches wide, so they fit perfectly between the studs of a timber frame house. The edges are trimmed, and now we have the familiar product before us. And here, another bit of magic happens: packaging. The finished mats or rolls are fed onto the packaging line. A special press compresses them, removing nearly all the air. The product's volume can shrink several times over. Then this compressed block is quickly wrapped in robust polythene film and heat-sealed.
This is done to save an enormous amount of space during transport and storage. It's rather like a vacuum bag for clothes. Instead of a huge, fluffy roll, we end up with a dense, compact package. And when the builder on site cuts through the film, the mineral wool hisses as it draws in air and, like a spring, expands back to its original size within a matter of seconds. The finished packages are stacked onto pallets by robotic arms, wrapped in stretch film, and forklifts carry them off to the warehouse or straight into the back of a lorry. And so, as yet another lorry rolls out through the factory gates, our journey comes to an end. We followed how ordinary solid rock, having passed through the fiery heart of the furnace, became a high-tech cocoon that would preserve warmth, silence, and safety in someone's home for many decades to come.
Now for the most fascinating bit, the environmental credentials, because this is where mineral wool absolutely smashes expectations. We've already mentioned it's made from rock and slag. Well, here's the thing. On average, modern mineral wool contains 70% recycled materials. Sometimes that figure reaches as high as 90%. Just imagine, 3/4 of your insulation is essentially industrial waste that's been given a second life. We're talking about millions of tons of metallurgical slag that used to simply end up in landfills, now transformed into a high-tech product. It's one of the finest examples of a circular economy, where one industry's waste becomes another's treasure. Manufacturing giants like Rockwool or Owens Corning process so much slag each year, you could fill thousands of Olympic-sized swimming pools with it.
But that's not all. The second superpower is acoustics. Due to its dense, chaotic fiber structure, mineral wool is an incredible sound insulator. It doesn't just block sound, it absorbs it. When sound waves enter the material's depth, they're forced to navigate through a labyrinth of billions of stone fibers, losing their energy and fading away. That's precisely why it's beloved not only in residential homes for protection from noisy neighbors, but also in professional recording studios, cinemas, and even between floors to avoid hearing footsteps from above. It's like building a personal silent mode into your walls. And finally, the mystery promised at the beginning. Despite mineral wool appearing soft, each of its fibers is a microscopic stone needle. When working with it, these needles can cause mechanical skin irritation, that very itch. And whilst modern technology has made the fibers safer, this stone fluff will always remind you of its true, hard nature, demanding respect and caution.
What if I told you there's a metal that flows like water at room temperature, killed thousands of workers during the colonial era, and without which gold mining would be impossible? A metal that vaporizes at 1100 degrees Fahrenheit and condenses back into liquid silver? Every year, the world produces around 1,300 tons of mercury, but that's nothing compared to historical scales. Over the last 500 years, humanity has extracted about 1 million tons of mercury from the Earth's depths. Half of that million was used before 1925. Mercury is obtained from red ore, cinnabar, by heating it to 900 to 1100 degrees Fahrenheit. During this process, mercury sulfide breaks down, releasing mercury vapors and sulfur dioxide gas. China dominates production, 95% of the world's mercury. In 2022, China produced 2,000 tons of mercury. A standard flask holds 76 pounds of mercury. These were the exact flasks used to ship it to gold mines during the gold rush. Stick around till the end. You'll discover a secret that even those who work with this metal won't talk about. Picture an underground mine somewhere in China, Kyrgyzstan, or Mexico, the world's biggest mercury producers. Deep beneath the surface, in the dim glow of miners' lamps, red streaks appear in the rock. This is cinnabar, mercury sulfide, a bright red mineral that humanity has known for thousands of years. The ancient Romans mined it both as a pigment and for mercury. The ancient Egyptians were using mercury as far back as 1500 BC. Greek philosopher Aristotle in 350 BC described how cinnabar was heated to extract mercury for religious ceremonies. Cinnabar forms in veins associated with volcanic activity and hot springs. About 90% of deposits require underground mining with tunnels. The remaining 10% can be extracted through open-pit methods. Cinnabar is separated from the surrounding rock through drilling and blasting or using powerful machinery. The ore is hauled out of the mine on conveyor belts or in trucks. Because cinnabar is a relatively concentrated ore, it can be processed directly without intermediate steps to remove waste rock. The ore is first crushed in one or more cone crushers. A cone crusher consists of an inner cone rotating on an eccentric vertical axis inside a stationary outer cone. When ore is fed into the top of the crusher, it gets squeezed between the two cones and breaks into smaller pieces. For concentrating low-grade cinnabar with a specific gravity of 8 to 8.2, gravity and flotation methods are used. Grinding to -48 mesh is the economically viable liberation point for the mineral. Some operations use mineral jigs to recover coarse heavy mineral and any metallic mercury that might be present in the ore. Flotation with one or more cleaning stages is used to produce a high-grade concentrate. It's not uncommon to obtain concentrates containing 40 to 50% mercury from ores containing 5 to 15 pounds of metal per ton. The concentration ratio is therefore high. The dewatered concentrate from flotation is combined and stored for roasting and recovery of metallic mercury. Now comes the most critical and dangerous stage, roasting. Cinnabar concentrate gets loaded into specialized furnaces. These can be multi-hearth furnaces, where ore mechanically moves down through a vertical shaft from one level to another via slowly rotating rakes. Or rotary kilns, where ore tumbles along the length of a long rotating cylinder, tilted a few degrees from horizontal. Either way, heat comes from burning natural gas or other fuel at the bottom of the furnace. Heated cinnabar reacts with oxygen in the air at temperatures ranging from 930 to 1,110 degrees Fahrenheit. A chemical reaction occurs. Mercury sulfide breaks down into sulfur dioxide gas and mercury vapor. Mercury rises as vapor. This is called roasting. Mercury vapors rise upward and exit the furnace along with sulfur dioxide, water vapor, and other combustion products. Significant amounts of fine dust from the crushed ore also get carried away and must be separated and captured. Next comes condensation. Hot gases containing mercury vapor pass through a cooling system. A condensation column is used, a special device where the vapors cool down and mercury condenses back into liquid metal. Pure mercury separates from sulfur in this process and evaporates easily. The condensation column collects the liquid metal. Thanks to mercury's high specific gravity, impurities gather on the surface and can be easily removed. The liquid mercury gets poured into standard iron flasks. Each flask holds 76 pounds of mercury. That's the standard unit of sale. These exact flasks shipped mercury to gold mines during the gold rush in California and Nevada in the 18th and 19th centuries. The process is simple in essence, with one drawback: toxic fumes. If roasting is done incorrectly, mercury vapors, which are highly toxic, can get released into the atmosphere. This was catastrophic for workers in the colonial era. The history of mercury production is full of tragedies. In 1564, cinnabar mining began in Huancavelica, Peru. With a local source of mercury, the amalgamation process was adopted for refining silver in Potosi, Bolivia, in the early 1570s. As a result, massive quantities of mercury were released into the environment. Between 1564 and 1810, approximately 17,000 tons of mercury vapor were released into the atmosphere in Huancavelica and 39,000 tons in Potosi. In 1604, an advocate for indigenous people described how fumes, dust, and candle smoke in the mine caused coughing and Huancavelica disease, and argued that forcing people to work in mercury mines meant sending them to a slaughterhouse. In 1630, a contemporary described the mines as a living image of death and a dark shadow of hell. The Jesuit José de Acosta, around 1590, wrote about the roasting process. If the smoke or fumes reach the people opening the pots, they get mercury poisoning and die, or are left in very poor condition or lose their teeth. The largest mercury deposit in history? Almaden in Spain. It was worked from Roman times until 1989, the world's biggest producer. In 2000, Almaden yielded 236 tons of mercury. Other major deposits: Khyber Khan in Kyrgyzstan, 550 tons, Algeria, 240 tons. During World War II, mercury production was critical. Mercury fulminate was essential for bullet primers, and the biggest producing region in Spain was under dictator Franco's control. The U.S. ramped up domestic production from 1941 to 1944. The price per flask during the war years averaged around $380 in 1960 prices. Today, global mercury production has plummeted. In 2016, they produced 4,500 tons, but in 2023, just 1,200 tons. China dominates with 95% of world production, 1,000 tons in 2023. Mercury has diverse applications, but its use is declining due to toxicity. Mercury easily forms amalgams with other metals, making it useful for extracting gold and silver. Much of the incentive to develop mercury deposits in the United States arose after the discovery of gold and silver in California and other western states in 1800. When mercury mixes with gold slurry, it triggers a reaction that separates gold from ore. This amalgam is then heated to vaporize the mercury and leave behind gold nuggets. Artisanal and small-scale gold mining is the largest source of anthropogenic mercury emissions, accounting for 38% of global releases. Other applications include chlorine and caustic soda production in mercury cell electrolysis plants. Until recently, this was a major consumer. In 2023, only one such facility was operating in the U.S. electrical devices: fluorescent and mercury vapor lamps, mercury batteries, switches, and relays. Measuring instruments, thermometers, barometers, pressure gauges. Dental amalgam, a mixture of mercury with silver and other metals for fillings. But because of its high toxicity, mercury use has dropped sharply over the last 20 years. Inhaling mercury vapor is especially dangerous for the kidneys, central nervous system, respiratory and cardiovascular systems. Inhaling mercury vapor also causes neurobehavioral disorders like hand tremors and mental impairment. Exposure to other forms of mercury, particularly methylmercury, which accumulates in fish, can also lead to kidney problems, lung issues, and central nervous system damage, as well as arthritis, reproductive problems, memory loss, psychosis, and in some cases, death. The United States banned the export of elemental mercury on January 1, 2013, under the Mercury Export Ban Act of 2008. Global mercury resources are estimated at around 600,000 tons, mostly in China, Kyrgyzstan, Mexico, Peru, Russia, Slovenia, Spain, and Ukraine. And so, having traveled from red cinnabar ore through roasting at 1100 degrees Fahrenheit, through evaporation and condensation, through the tragedies of thousands of workers in the colonial era, through the gold rush and world wars, emerges a liquid metal that flows at room temperature, without which gold mining would be impossible, but which has killed more people than any other metal in human history.
Every year, more than 50,000 tons of uranium are mined across the globe. But to extract just a few grams of its energy, mountains of rock must be moved. It's a journey that begins in a desert where the temperature hits 38 degrees Celsius and ends inside a reactor that powers New York City. It involves centrifuges that spin faster than a jet turbine and chemicals that can dissolve metal in seconds. But the most interesting part is something that even the safety manuals don't mention. Watch until the end and you will learn a secret that will change how you think about nuclear power forever. It all begins in the dust, literally. Uranium ore is mined in hot, arid regions: Arizona, Wyoming, Texas, New Mexico. Here, the sun is relentless, reaching 38 degrees Celsius in the shade, if you can find any. There are two main extraction methods: open pit mining, where the topsoil is stripped away, and underground mining, with explosives and hoists. There is also a third, more subtle technique: in situ leaching. Pipes are drilled deep into the earth. Special solutions are pumped down to dissolve the uranium directly from the rock, and the resulting liquid is then pumped back to the surface. The ore itself, a grayish-brown rock, looks unremarkable, but within it, the crucial isotope uranium-235 makes up just 0.7%. The rest is a vast, almost useless mass that is inert in a reactor. And to squeeze the required drop of energy from it, hundreds of tons must be processed. After mining, the ore is crushed, milled into a fine powder, and thrown into a chemical bath of acid or alkaline solutions. This is followed by filtration, precipitation, and drying at 260 degrees. The final product is yellow cake, a bright yellow uranium concentrate. Officially, it's known as uranium ore concentrate, but everyone at the plant just calls it yellow cake. It looks striking, a mustard-colored loose powder like a spice for a barbecue. But this is a substance you must not touch and must never inhale. It emits alpha radiation, has a long half-life, and its dust is dangerously toxic. The yellow cake is sealed in double-walled drums, loaded onto escorted trailers, and plastered with radiation warning signs for the journey to the enrichment facility. This is the start of the path that turns a poisonous dust into the clean white light from a lamp over your kitchen table, or the electricity that powers the tube deep beneath London. Right, the yellow cake has arrived. It's radioactive, dry, and sealed in its drum. The next step? Turn it into a gas. And not just any gas. This is uranium hexafluoride. The uranium concentrate is first dissolved in acid, purified, and converted into uranium dioxide. And here, the alchemy begins. The uranium dioxide is treated with fluorine gas in special reactors at 540 degrees. The reaction creates a volatile, transparent gas that boils at just 56 degrees. A little heat, and it turns from solid crystals into a vapor. But it's not that simple. This gas is extraordinarily toxic. It corrodes most metals, destroys human tissue, and on contact with humid air, it instantly transforms into hydrofluoric acid and uranyl fluoride, a lethal cocktail. That is why this entire process is conducted inside sealed, automated reactors. The substance is stored as solid, whitish crystals, formed by cooling it to room temperature. These crystals are kept in steel cylinders, each engraved with a serial number and a radioactive symbol. A single cylinder weighs almost 14 tons. You think your washing machine spins fast? You haven't seen a nuclear centrifuge. They can reach 70,000 revolutions per minute, more than 10 times faster than a jet engine turbine. And all for one purpose: to separate uranium isotopes. Uranium hexafluoride, that toxic gas we just created, is fed into a tall, narrow cylindrical chamber, which is then spun at an insane speed. Centrifugal force does the work. The heavier uranium-238 atoms are flung towards the outer wall, while the lighter, crucial uranium-235 atoms remain closer to the center. But one centrifuge isn't enough. They are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas and passes it to the next. This process is repeated, cycle after cycle, until the concentration of uranium-235 reaches at least 3 to 5%. This is the standard grade for reactor fuel. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it is converted back into a solid, this time a ceramic form. After a series of chemical reactions, the gas becomes uranium dioxide powder, a dark gray solid. This powder is pressed under 20 tons of pressure into small cylindrical pellets, just 8 millimeters in diameter. They look almost harmless. Next, the pellets are centered in a furnace at nearly 1650 degrees, making them as hard as porcelain. They are then polished and ground to precise dimensions. The finished pellets are loaded into long metal tubes known as fuel rods, typically made of a zirconium alloy because it resists corrosion and can withstand intense radiation. Each rod holds over 300 pellets. The rods are hermetically sealed and then bundled together into modules called fuel assemblies. They look like a square frame holding a grid of several dozen rods. A single assembly can weigh over 680 kilograms and will operate inside a reactor for up to 6 years. The finished fuel is packed into armored containers for transport. The journey is made under guard, on a special route with a security escort and GPS tracking. Left over from all of this is the depleted uranium hexafluoride, known as tails. It's a mix of isotopes with a small amount of U-235 remaining, but not enough to be useful. These tails are stored in steel cylinders at designated secure sites. When a fuel assembly has served its 4 to 6 years in the heart of the reactor, it is no longer a shining star. It is removed by a robotic system and moved into a deep pool of water, over 6 meters deep. The water cools the assembly and shields the intense radiation because the fuel is still incredibly hot. It rests there for several years. After that, it has 2 possible futures: long-term dry storage in concrete and steel casks, or reprocessing. This usually happens in other countries, as the US and UK primarily store their waste rather than reprocess it. In a dry storage facility, the assemblies stand for decades, cooled by natural air convection, as if in a nuclear monastery. This isn't the end, but a new phase of life. A slow, controlled existence, but one deeply connected to the future of energy. Because even after its time in a reactor, this fuel remains a source of heat, a lesson in engineering, and a reason for profound respect.
Imagine a part so perfect it can spin for 30 years without stopping. From tiny balls just an eighth of an inch across to giants 30 feet tall holding up wind turbines, bearings are a $120 billion a year industry. But their life begins in absolute chaos. Massive explosions, hellish fire, pressure that could crush a tank. How does raw metal become the heart of perfection? Today you'll follow the complete journey, from a quarry blast to the perfect ball spinning at 10,000 revolutions per minute. If you want to see how chaos turns into precision, subscribe to the channel. Here we show the manufacturing that builds our world. It all starts with a roar that shakes the ground for miles around. In the giant quarries of Australia and Brazil, iron ore hides in layers of rock hundreds of feet thick. Geologists turn the quarry into a chessboard. They drill boreholes 60 to 100 feet deep. Borehole diameter, 10 inches. Distance between boreholes, 16 feet. 1 square mile, 1,000 boreholes. Into each they pour explosives, a mix of ammonium nitrate and diesel fuel. Ratio 94 to 6%. Charge weight per borehole, 650 pounds. Detonation happens with millisecond delays. First borehole explodes. 20 milliseconds later, the second. 40 milliseconds, the third. The wave rolls across the entire field. In 10 seconds, they detonate 200 boreholes. They blast 3.5 million cubic feet of rock, energy equivalent to 110,000 pounds of TNT. But this isn't random chaos. This is planned destruction. Chunks of rock shoot 150 feet into the air. They fall. Dust rises over half a mile into the sky. When it settles, instead of a mountain, there lies 2 million tons of crushed ore. Giant excavators roll onto the site. The excavator bucket? 1,400 cubic feet. That's the volume of a small apartment. The bucket weighs 28 tons. One scoop? 100 tons of rock. They load it into dump trucks. Hauling capacity of each truck, 360 tons. Wheel height, 13 feet. Diameter, 11.5 feet. Weight of one wheel, 5 tons. Engine, 3,500 horsepower. Fuel consumption, 35 gallons per mile. The dump truck hauls ore to the crusher. Distance, 9 miles. Speed, 25 miles per hour. Travel time, 20 minutes. In one day, a single truck makes 30 trips, hauls 10,000 tons. 20 excavators and 60 dump trucks work the quarry. They move 300,000 tons of ore per day. That's 100 million tons a year. Crushing. Ore enters the jaw crusher. The crusher's mouth, 13 feet wide. The jaw weighs 120 tons. Jaw stroke, 12 inches. Oscillation frequency, 200 strikes per minute. Drive power, 1.5 megawatts. The crusher pulverizes yard-wide rocks into 8-inch chunks. Throughput, 2,000 tons per hour. From the jaw crusher, ore moves to the cone crusher. The cone spins inside the bowl at 150 revolutions per minute. Gap between cone and bowl, 1 inch. 8-inch pieces become 1-inch pieces. Then, the ball mill. Cylinder 20 feet in diameter. Length, 26 feet. Inside, steel balls. Ball diameter, 4 inches. Weight per ball, 9 pounds. Total balls, 50,000. Combined weight, 200 tons. The mill rotates at 18 revolutions per minute. Balls drop from 6.5 feet. Impact grinds ore to powder. Particle size after milling, 0.04 inches. The thickness of a human hair. Thickness. Flotation enrichment. Ore powder gets mixed with water, creates a slurry. Solid concentration, 30%. Add reagents. Potassium xanthate, 7 ounces per ton of ore. Pine oil, 1.8 ounces per ton. Xanthate makes iron particles hydrophobic. They repel water. Pour the slurry into the flotation machine. Tank volume, 13,000 gallons. Air pumps in from below. Pressure, 30 pounds per square inch. Flow rate, 10,000 cubic feet per hour. Air forms billions of bubbles 0.2 inches across. Bubbles stick to iron particles. Lift them up. Foam forms on the surface. Reddish gray. Dense. Iron content in the foam, 67%. Waste rock sinks to the bottom. Gets pumped out and dumped in tailings. Foam scraped off with blades, sent to filtration. Vacuum filter sucks out the water. Leaves a damp mass. Moisture content, 9%. That's concentrate. Gets turned into pellets. Pelletizing. The concentrate goes to a disc pelletizer. The disc is 15 feet across, tilted at 45 degrees, spins at 15 revolutions per minute. Powder feeds onto the disc. Water's added, 3% by weight. Centrifugal force rolls the powder into balls. Pellets come out ½ inch in diameter, give or take 1/16 of an inch. The pellets roll off the edge onto a conveyor. Output? 300 tons an hour. 1 million pellets every hour. The pellets head to the kiln. Firing temperature, 2450 degrees Fahrenheit. 20 minutes in the heat. The pellets turn rock hard. Crushing strength, 3,500 psi. Now they're ready for the blast furnace. Blast furnace smelting. Pellets are loaded into the blast furnace. The furnace stands 105 feet tall. The throat diameter, 40 feet. The hearth diameter, 26 feet. Furnace volume, 42,000 cubic feet. Loaded in layers. Pellet layer, 3 feet. Coke layer, 20 inches. Limestone layer, 8 inches. Hot air blasts in from below. Temperature, 2,200 degrees. Pressure, 60 pounds per square inch. Flow rate, 100,000 cubic feet per minute. The coke burns, carbon monoxide releases. It strips the iron from the pellets. Temperature in the hearth, 3,600 degrees. The iron melts, flows downward, pools in the hearth. Every 4 hours they tap the pig iron. They open the tap hole. Pig iron pours out like a river of fire. Temperature at 2,700 degrees. Color, bright orange. One tap, 300 tons. In 24 hours, the furnace produces 2,000 tons of pig iron. The pig iron contains 4% carbon. That's way too much. Pig iron's brittle. Needs converter smelting. Steel production. They pour pig iron into an oxygen converter. The converter holds 350 tons. A lance descends from above. The lance is 20 inches across. Pure oxygen blasts through the lance. Pressure hits 175 pounds per square inch. Flow rate, 18,000 cubic feet per minute. Jet velocity, 1,300 miles per hour. That's twice the speed of sound. Oxygen oxidizes the carbon burns. Turns into carbon dioxide. Flame shoots out the converter's mouth. Flame reaches 30 feet high. Temperature hits 3,600 degrees. The process takes 20 minutes. Carbon content drops from 4% down to 0.7%. This is bearing steel. Grade designation SAE 52100. Chromium content 1.5%. Chromium provides hardness and wear resistance. They pour the steel into a ladle. From the ladle into molds. Out come ingots, blanks weighing 5 tons each. Ingot dimensions 3 feet by 3 feet by 6 feet. Rolling and machining. Ingots are heated in a furnace to 2,200 degrees Fahrenheit. Rolled on a mill. Rollers 40 inches in diameter. Rolling force 2,000 tons. The ingot becomes rods 4 inches across. Rod length 20 feet. Rods are cut into blanks 8 inches long. Blanks are heated to 1,560 degrees. Stamped into rings on a press generating 1,200 tons of force. You get a ring with an outer diameter of 4 inches. Inner diameter, 3.1 inches. Height, 0.8 inches. Rings undergo heat treatment. Heated to 1540 degrees. Held 30 minutes. Quenched in oil at 140 degrees. Cooling rate, 540 degrees per second. Tempered at 360 degrees for 2 hours. Hardness after heat treatment, 62 Rockwell. Then, grinding. The ring is clamped in a lathe chuck. The abrasive wheel spins at 100 feet per second. Removes a metal layer 0.004 inches thick per pass. Surface roughness, 0.08 millionths of an inch. That's 10 times smoother than glass. Deviation from roundness, no more than 0.08 thousandths of an inch. Balls are made by cold heading. Wire 1/2 inch in diameter is cut into 1/2 inch segments. Each segment is clamped between 2 dies. Pressure, 2 tons. The segment deforms into a sphere. You get a rough ball? It's ground between 2 cast iron discs. The discs rotate toward each other. Speed, 200 revolutions per minute. Between the discs, abrasive paste. Grit size, 40 micrometers. Grinding takes an hour. The ball shrinks by 0.012 inches. Final diameter, 0.46 inches. Deviation, plus or minus 0.004 hundredths of an inch. Sphericity, 0.08 thousandths. Roughness, 0.02 millionths of an inch. Bearing assembly. Inner ring, outer ring, 17 balls. Brass separator, lithium grease. Bearings done. It'll spin for 30 years, 1 billion revolutions.
Every single day, the United States alone extracts over 9 million barrels of oil. A single barrel holds nearly 159 liters. Now multiply that by thousands of wells across the planet. But have you ever stopped to consider what oil actually is and how it is formed? This isn't just a black liquid. It is the result of immense geological forces acting over millions of years deep within the earth. Oil is born from the remains of ancient life, transformed by pressure and heat into a liquid hydrocarbon. And from there, the modern story begins. A high-stakes hunt, deep earth drilling, and the incredible process that turns this primordial substance into the fuel that moves our world. It's expected that the average daily oil output in the U.S. will soon reach 9.9 million barrels. But what exactly is this substance we call oil? The process of its formation is a slow, powerful saga that unfolds over geological time. It begins with the accumulation of organic material, the remains of ancient plants and animals at the bottom of seas and lakes. Over millions of years, these remains are buried under layers of sediment. Under the immense pressure and heat, this organic matter transforms into a waxy substance called kerogen. Further heating, in a temperature window between 60 and 150 degrees Celsius, triggers the thermal breakdown of kerogen, creating liquid hydrocarbons. And that is what oil is, the distilled essence of ancient life. Once formed, this oil migrates through porous rock until it reaches a geological trap, a structure that blocks its path. Here, it accumulates, forming a reservoir. To find these hidden reservoirs, we must first understand the earth beneath our feet. This is the world of geological surveying, one of the most complex and expensive stages of the process. Scientists use satellite imagery, magnetometers, and seismic waves. Seismic surveying is particularly spectacular. Controlled underground explosions are triggered to send shock waves deep into the earth. By reading the echoes, geologists can map the subterranean landscape and identify potential traps. When a promising zone is identified, the drilling begins. A land or offshore rig becomes a giant mechanical creature operating day and night without pause. The drill string, steel pipes with a cutting bit at the end, bites into the earth, rotating at up to 200 revolutions per minute. A special drilling fluid is pumped down to lubricate the bit and carry rock cuttings back to the surface. A modern well can reach depths of 3 to 5 kilometers, and in some cases 10 or even 12. In Texas or Saudi Arabia, wells are drilled over 8 kilometers long, often with a significant horizontal section to maximize contact with the reservoir. A single drilling operation can cost tens of millions of dollars with no guarantee of success. But when a well strikes oil, it begins its journey to the surface, either under its own pressure or with the help of powerful pumps. Saudi Arabia is one of the world's oil titans. In February, the kingdom was producing nearly 9 million barrels per day, and its position is only set to strengthen, as Saudi Aramco has recently discovered 14 new oil and gas fields. Once the well is completed, the extraction phase begins. In a rich reservoir, the natural pressure is enough to force the oil to the surface. This is known as a gusher, and while it looks impressive, it's now considered an outdated and dangerous method. Modern wells are fitted with complex valve systems, known as Christmas trees, that allow for precise control of the flow. The crude oil emerges and is sent to a processing facility where it is separated from natural gas, water, sand, and other impurities. This often happens right at the well site. The separation is a fascinating process. The mixture enters a large sealed vessel where gravity takes over. The lighter gas rises to the top while heavy water and sediment sink to the bottom. Sometimes, water is trapped in the oil as a microscopic emulsion, which is harder to separate. In this case, chemical de-emulsifiers are added to break it down. To maintain pressure in an aging reservoir, secondary recovery methods are used. Water or gas is injected into the formation through other wells to push the remaining oil towards the production well. These techniques can allow up to 60% of a reservoir's oil to be recovered. The average modern well in the U.S. produces between 500 and 1,500 barrels per day. A single barrel is 159 liters. Multiply that across thousands of wells and you begin to grasp the true scale of this global operation. Crude oil itself is a complex cocktail of hundreds of different hydrocarbons. To turn it into petrol, it must undergo a series of technically demanding stages at a refinery. It all starts with fractional distillation. The crude oil is heated to between 350 and 400 degrees Celsius and fed into a tall distillation column. The various components of the oil vaporize and rise to different heights inside the column before they cool, condense, and are drawn off. The petrol fraction is one of the lightest, and it's typically collected at a temperature between 40 and 200 degrees. But this initial distillation only yields about 15 to 20% petrol. To increase the yield, a process called cracking is used. This breaks down long, heavy hydrocarbon molecules into shorter, more valuable ones. The most common method is fluid catalytic cracking, where heavy fractions are heated to nearly 1,000 degrees in the presence of a catalyst. This allows for a much higher yield of petrol from the heavier residues. Hydrocracking, which uses hydrogen under high pressure, is also used. Ultimately, the petrol yield from a single ton of crude oil can be pushed as high as 40 or 50%. The petrol produced so far, however, has a low octane rating. To fix this, it undergoes reforming, a process that restructures the molecules at high temperatures using a platinum catalyst. In the final stage, additives are blended into the petrol to improve its properties: anti-corrosion agents, anti-knock compounds, and detergents. This ensures engine longevity, reduces harmful emissions, and improves efficiency. A single modern refinery can process up to 400,000 barrels of crude oil every single day. The sheer volume is staggering, especially when you consider that the daily petrol consumption in the U.S. alone is around 1.4 billion liters. A river of ancient life powering the modern world.
What you're witnessing here is something that would have made our grandfathers stop dead in their tracks and stare in absolute wonder. This is the forging of a massive rolling mill shaft for a steel plant weighing 5,700 pounds. That's almost 3 tons of solid steel being shaped by pure force and principles that are centuries old. The process starts with a massive steel ingot that's been heated in a gas furnace to around 2,200 degrees Fahrenheit, hot enough to glow like a miniature sun. Back in the days when American steel mills dotted the landscape from Pittsburgh to Gary, Indiana, this kind of work was the backbone of our industrial might. The forging press you're seeing here is a modern hydraulic giant capable of exerting thousands of tons of pressure. But the fundamental process hasn't changed since blacksmiths were shoeing horses on Main Street. Watch closely as the glowing workpiece gets positioned under the press. The operators, and these folks are true craftsmen, use overhead cranes and manipulators to rotate and position the workpiece with incredible precision. Every press strike, every controlled squeeze is carefully calculated. They're not just hammering hot metal, they're restructuring the grain structure of the steel, eliminating internal voids and creating a component that'll eventually face enormous forces in the rolling mill. The shaft gets worked from multiple angles, gradually taking shape. Between each pressing operation, the team repositions the workpiece, sometimes returning it to the furnace to maintain that critical working temperature. This dance between heat and pressure goes on for hours. The hydraulic press moves with deliberate force, almost gently despite its massive power. Around 5,000 to 10,000 tons of pressure compacts the steel's crystalline structure into something far stronger than the original ingot could ever be. What's fascinating is how this forged shaft will serve in a steel mill, helping shape other steel products. It's a beautiful cycle. Metal processing metal, and these shafts can last for years under extreme conditions. Today's technology, precise temperature control, computer-controlled press cycles, metallurgical analysis, ensures consistency our ancestors could only dream of. But the soul of the process remains unchanged. Heat, pressure, and the skilled hands of craftsmen who understand steel like old friends. Now here's something that combines brute force with surprising delicacy. The process of coiling a 2-inch spring bar. If you've ever wondered how these massive industrial springs are made, the ones that control freight train suspension or support heavy machinery, you're about to get a lesson. The process starts with raw stock, in this case a solid 2-inch diameter rod of heat-treated spring steel. This isn't ordinary metal. It's been precisely engineered to have the exact balance of hardness and flexibility. Too hard, and it'll snap like a pretzel. Too soft, and it won't spring back properly. Watch as the rod feeds into the coiling machine. The machine grabs one end, while a massive rotating mandrel, essentially a former, begins bending the rod around its circumference. The force required here is substantial. We're talking about permanently deforming 2-inch steel, which demands hydraulic power in the range of several hundred tons. The mandrel size determines the spring's inner diameter, and precision here is critical. As the coiling progresses, you'll notice how smoothly the rod bends despite its thickness. This is achieved through controlled feed rates and constant pressure. The machine maintains tension while rotating, creating consistent spacing between coils. Back in the 30s and 40s, this kind of work was done by hand with tremendous effort, using heat and mechanical advantage. Modern CNC systems can produce springs with tolerances measured in thousandths of an inch. What you're seeing here is one of the most reliable welding processes ever developed: submerged arc welding. This technique has been joining heavy steel since the 1930s. Here's what makes this process so special. Unlike stick welding, which your grandfather might have done in his garage, or even modern semi-automatic welding, submerged arc welding happens beneath a blanket of granulated flux. This flux, which looks almost like coarse sand, performs several critical functions. It shields the molten weld pool from atmospheric contamination, prevents oxidation, and actually contributes to the chemistry of the weld itself. The setup is mesmerizing. A continuously fed wire electrode runs through the welding head, and when it strikes an arc to the base metal, it melts both the electrode wire and the parent material, creating a deeply penetrating weld. But you can't see any of this happening because it's all taking place under that protective layer of flux. The flux melts on top, forming a protective slag that operators chip off later. Watch the welding head move along the joint. It's typically automated for consistency. The process can deposit weld metal at rates that would make a stick welder cry with envy, 10 to 50 pounds per hour depending on the setup. That's why submerged arc welding is the #1 choice for welding thick sections in shipbuilding, pressure vessel fabrication, and structural steelwork. The beauty of this process lies in its depth of penetration. Submerged arc welding can achieve full penetration welds on steel up to 3/4 of an inch thick in a single pass. Now, let's look at modern hot forging, a process that's adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small-batch artisanal blacksmithing. The process begins with steel blanks, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion. But within seconds, a steel blank placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2000 and 2300 degrees Fahrenheit, depending on the steel grade, the blank is transferred to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. Excess material, called flash, gets squeezed out around the edges and is later trimmed off. What's remarkable is the speed and precision of modern forging presses, machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. Sometimes you need to bend metal that's so big it seems almost impossible, and that's exactly what a horizontal bending press specializes in, forming massive pipes that can be several feet in diameter. The problem with bending large pipes is avoiding what we call wrinkling on the inside radius and tearing on the outside radius. The system solves this through controlled hydraulic pressure applied by a precisely formed die that supports the pipe during the bending process. Watch as the massive pipe gets positioned in the machine. That positioning alone requires overhead cranes and careful alignment. The bending die, often weighing several tons itself, presses against the pipe while it's supported at both ends. The hydraulic system applies hundreds of tons of force, gradually bending the pipe through the desired angle. Even with pipes this size, the bend radius, angle, and final dimensions can be controlled to surprisingly tight tolerances. These bent pipes end up in industrial piping systems, structural applications, and even shipbuilding. We're watching the cutting of a heavy railroad rail, 47 kilograms per meter, which translates to roughly 95 pounds per yard, using oxy-fuel cutting with propane. The oxy-propane torch system operates on a principle that's elegantly simple, yet demands real skill to execute properly. The propane flame, mixed with oxygen in the torch's preheat nozzles, heats a spot on the steel to ignition temperature, around 1600 degrees Fahrenheit for steel. Once that critical temperature is reached, a stream of pure oxygen under high pressure is introduced through the cutting nozzle. Here's the beautiful part. The oxygen doesn't melt the steel, it actually oxidizes it. The steel burns in the oxygen stream, and the force of that oxygen jet blows the molten iron oxide out of the cut, creating the kerf. The operator maintains a specific distance from the workpiece, the gap between the torch tip and the work surface, typically around 1/8 to 1/4 inch. Too close, and the tip will clog with splatter. Too far, and the cut becomes ragged. For cutting rail, you'll notice the torch follows the rail's profile. The rail has this characteristic mushroom shape: wide base, narrow web, and heavy head on top. Each section has different thickness, so cutting speed must be adjusted accordingly. We're now entering the realm of precision machining, where tolerances are measured in 10,000ths of an inch, and programming is just as critical as the actual technique. What you're witnessing is CNC milling of optical chuck jaws, programmed using CAM software, and this represents the perfect marriage of computer manufacturing and skilled craftsmanship. The process begins in the CAM software. A programmer working from engineering drawings creates a three-dimensional model of the chuck jaw, then generates the tool paths that will machine it. The program calculates optimal cutting strategies, selecting appropriate tools, determining feed rates and spindle speeds, and simulating the entire process virtually to catch any potential collisions or errors before a single chip is cut. Watch the CNC mill executing these programmed tool paths. This is likely a high-precision vertical machining center, equipped with a spindle that can rotate at 10,000 RPM or more while maintaining accuracy. Instead of plunging straight down, the tool follows spiral and trochoidal paths that maintain constant chip load and reduce tool wear. Notice the surface finish developing on the chuck jaw faces. These are critical contact surfaces that will grip workpieces, and they must be flat within microns and properly finished to avoid damaging delicate components. The float glass process you're watching, one of those manufacturing breakthroughs that completely transformed the industry, and remarkably, the core principle hasn't changed since it was invented back in the 1950s. Here's how this incredible process works. Molten glass, heated to around 2000 degrees Fahrenheit, flows continuously from the furnace onto the surface of a molten tin bath. The glass literally floats on the tin, spreading under gravity and surface tension, forming a ribbon with parallel surfaces and uniform thickness. Watch as the glass ribbon advances through the tin bath. Temperature is carefully controlled, gradually cooling as the glass moves forward. This controlled cooling, called annealing, is critical. It relieves internal stresses that would otherwise cause the glass to crack or shatter during cutting or installation. As the glass exits the tin bath, it's cool enough to be supported by rollers, entering what's called a layer, a long cooling tunnel where temperature continues to drop under precise control. The glass emerges at room temperature, perfectly flat with optical clarity that would have been impossible to achieve consistently using the old methods of sheet glass production. The production line can create thousands of square feet of glass daily, all with consistent quality. The ribbon is then cut to size, inspected, and prepared for further processing like tempering or coating.
Picture a chunk of metal weighing 130 tons, the size of a 3-story building, spinning at 100 revolutions per minute. This is a supertanker's propeller, the most powerful driving force ever created by humans. Every second, this propeller pushes 200,000 tons of cargo forward. A single sweep of its blade generates the power of 50 cars. But here's the most incredible part. This giant is cast as a single monolith. No welding, no bolts. One solid piece of bronze or steel. How did humanity learn to cast metal structures the size of a house? You'll discover why a propeller like this takes 2 weeks to cool, how it's machined for 3 weeks, and why the tiniest crack could send a ship to the bottom. Watch until the end. The finale reveals the scale of engineering madness that moves the oceans. This is the story of how titans of the seas are born.
The history of the propeller began in the early 19th century. Before that, ships moved either under sail, by oars, or using paddle wheels. Paddle wheels were inefficient. Half the energy was wasted. In 1836, British farmer and inventor Francis Pettit Smith patented the screw propeller. The idea was simple. Rotating blades screw into the water like a corkscrew into a cork, pushing the ship forward. Early propellers were small, 4 to 5 feet in diameter, made from wood or cast iron. But as ships grew larger, so did the propellers. By the early 20th century, steel steamships over 300 feet long appeared. They required propellers 10 to 13 feet in diameter. And with the arrival of supertankers and container ships in the mid-20th century, propeller sizes reached incredible proportions. Modern ocean giants stretching 1,300 feet need propellers 26 to 33 feet in diameter. That's the height of a 3-story building.
The world's largest propeller was built for the Emma Maersk container ship, one of the biggest vessels on the planet. The propeller's diameter? 31.5 feet. Weight? 131 tons. That's 2 tanks combined, or 17 elephants. The propeller has 6 blades, each the size of a car. Total blade surface area? About 750 square feet, like a big apartment. The ship's engine produces 109,000 horsepower. All that power flows through a single propeller. At full speed, the blade tips slice through water at 125 miles per hour. Water pressure on the blades? Dozens of tons per square foot. Any crack, any casting flaw, and centrifugal force rips the propeller apart. The ship's dead in the middle of the ocean. That's why manufacturing these propellers is the pinnacle of metallurgy and engineering. The slightest mistake is unacceptable.
Where and how do they make these monsters? The largest propeller manufacturers are in Japan, South Korea, China, Germany, and the Netherlands. The most famous include Japan's Nakashima, Germany's Mecklenburg Metallgas, and the Dutch Works4. They have foundries the size of a football field and cranes that can lift 200 tons. The process starts with design. Engineers calculate blade shapes on supercomputers. Angle of attack, curvature, thickness, everything affects efficiency. The propeller needs to create maximum thrust with minimal cavitation, the formation of water bubbles that destroy metal. The tiniest miscalculation and the propeller becomes inefficient or wears out fast. After the calculations, they create a full-size wooden model of the propeller. Yes, wood, 31 feet in diameter. Master craftsmen carve it for weeks using blueprints and templates, precision down to a millimeter. This wooden model becomes the foundation for creating the casting mold.
They coat the wooden pattern with a special compound and place it in a massive flask, a steel box the size of a room. Around the pattern, they pack in molding sand mixed with binding agents. The mixture gets packed layer by layer. Each layer is compacted through vibration and pressure. The process takes several days. Once the flask is full, they split the mold into 2 halves and carefully remove the wooden pattern. What remains is a cavity shaped like the propeller, a negative. They coat the interior surface of the mold with a refractory compound, so the molten metal won't damage the sand. Then they bolt both halves back together. The mold has to withstand the pressure of 130 tons of liquid metal. They install the gating system, channels that'll feed metal into the mold. It's calculated so the fill happens evenly, without air pockets or cold joints. The mold is ready. Now comes the really impressive part, melting the metal. In the foundry, there's a massive induction furnace, a steel crucible holding 40 cubic meters wrapped in electromagnetic coils. They load it with bronze or alloyed steel stock, bars, ingots, scrap. 140 tons of metal. That's with a buffer. Some will stay in the gates and risers. They flip the switch. Powerful electromagnets induce eddy currents in the metal. The metal starts heating from the inside. Temperature climbs to 1600 degrees Celsius. The metal melts, glows orange, then white. The surface churns. The crew skims off slag, oxides and impurities floating to the top. They add alloying elements, manganese, nickel, aluminum, for strength and corrosion resistance. They pull a sample of the melt, analyze the composition. When everything's ready, they start the pour. The furnace tilts with a special mechanism. Molten metal flows into a massive ladle suspended from an overhead crane. The ladle holds 140 tons. This is the most critical operation. The metal has to be uniform in composition and temperature. The crane moves the ladle toward the mold. The metal glows a blinding white, so bright you can't look at it without dark glasses. The temperature around it climbs to 140 degrees, even though the ladle's 30 feet away. Workers in silvery heat-resistant suits control the pour. They open the ladle gate. Molten metal flows into the gating system. First as a thin stream to preheat the channels. Then the flow gets stronger. The metal fills the mold from bottom to top, pushing air out through special ventilation channels. The pouring process takes about an hour. 300,000 pounds of liquid metal transfer from ladle to mold. When the mold is full, they close the ladle gate. The metal surface in the mold forms a crust of oxides. They dust it with a special powder that creates a protective layer. Now the waiting begins. The metal has to cool and solidify. But at this size, that's not quick. 260,000 pounds of bronze or steel cool slowly, very slowly. Two weeks, 14 days the mold sits untouched. Inside, crystallization slowly occurs. Molten metal transforms into solid. Temperature drops at a rate of a few degrees per hour. Cooling too fast leads to cracks from uneven shrinkage. Too slow, large metal grains form, reducing strength. Engineers monitor the process with thermocouples, temperature sensors embedded in the mold. After 2 weeks, they break open the mold. A crane lifts the flask, opens it up. The molding sand pours away, revealing the casting. Before their eyes, a giant propeller, covered in black scale. Weighs 150 tons, 20 tons more than the finished product. Excess metal has solidified in the gates, risers, and allowances. The propeller moves to a special stand. Machining begins, transforming the rough casting into a perfect ship's propeller. And that's another 3 weeks of work. First, they cut off the sprues and risers, solidified metal feed channels. They use gas torches and heavy-duty bandsaws. The cut-off chunks weigh several tons each. They'll go back to the melt shop too. Then rough machining begins on turning and milling machines. These are giant machines, a bed 20 meters long, a milling head weighing 10 tons. The propeller is clamped on a rotating table. Cutters remove the stock, excess metal left for machining. Chips fly off in spirals as thick as a finger. Tons of metal are removed per shift. They mill the hub, the central part of the propeller that fits onto the shaft. A hole about 3 to 5 feet in diameter has to be perfectly round and concentric, precision tenths of a millimeter. Then they machine the blades. Each blade is milled to a complex profile: leading edge, trailing edge, face, back. The profile changes from root to tip. It's a three-dimensional, doubly curved surface. The machine runs on computer control from a program based on design data. After roughing comes finishing. Fine-toothed cutters pass over the blade surfaces, removing fractions of a millimeter. The surface becomes smooth. Then polishing. Abrasive wheels buff the blades to a shine. This is critically important. Surface roughness increases water resistance and promotes cavitation. A perfect surface cuts a ship's fuel consumption by percentage points. For a supertanker, that's millions of dollars in savings per year. After machining, a propeller is weighed and balanced. The center of mass must lie exactly on the rotation axis. Otherwise, vibrations will develop during operation, destroying bearings and potentially damaging the ship's hull. Balancing is done by drilling small cavities in specific locations. The final operation, non-destructive testing. The propeller is X-rayed, checked with ultrasound, examined using magnetic particle inspection. They're looking for internal defects, voids, cracks, inclusions. If they find a critical defect, the propeller is scrapped. 287,000 pounds of metal and a month of work go to waste. The cost of such a propeller, $1 to $3 million. And just like that, making the journey from a wooden model through the hellish heat of 1600 degrees and 140 tons of molten metal, through 2 weeks of cooling and 3 weeks of machining on giant lathes, a propeller is born, the heart of a supertanker, the pulse of an ocean giant. A solid piece of metal the size of a house, weighing 130 tons, capable of transmitting 100,000 horsepower. It's a triumph of engineering brilliance and metallurgical mastery. Every time you spot a container ship on the horizon or an oil tanker in port, know this: beneath the water spins a titan, born in fire and honed to perfection. A monolith of bronze or steel, every square inch of which withstands tons of pressure. A propeller that drives forward half the world's trade. 90% of all cargo moves by sea. This is a story about giants created by humans, about how humanity learned to cast metal the size of a house and machine it with precision down to a millimeter. A propeller isn't just a chunk of metal. It's a symbol of man's dominion over the oceans, a symbol of the technology that connected continents. From wooden model to steel reality, a journey spanning 5 weeks and millions of dollars. A journey repeated hundreds of times a year in foundries across the world, so the planet's fleet keeps pushing forward.
Every year, hundreds of oil platforms get installed in the world's oceans. Each one weighs tens of thousands of tons, and at some point, all that weight hangs from a single hook. Not a cable, not a beam, but a hook. A piece of forged steel that looks like a giant fishing hook from another dimension. Around it, the North Sea, a storm, 30-foot waves, a crane swaying on the deck of a ship, and the hook holds. It holds 8,000 tons. That's roughly the weight of 8,000 cars lifted simultaneously above the water's surface. One invisible microcrack half a millimeter wide, and a structure worth billions of euros plunges to the bottom, along with everything attached to it. How do you forge a monster capable of holding 10,000 tons in the middle of a raging ocean from molten steel, at temperatures exceeding 4,000 degrees Fahrenheit? And what critical moment do manufacturers carefully hide from prying eyes? Watch until the end. The answer will surprise you. It all starts with choosing the metal. For giant crane hooks, they use special structural steel where the carbon content doesn't exceed 1%, while chromium additives up to 2% and molybdenum up to 0.5% deliver tensile strength. exceeding 145,000 pounds per square inch. These elements aren't chosen randomly. Chromium provides corrosion resistance for marine conditions, and molybdenum prevents brittleness at low temperatures because a hook might operate in the North Sea, where in winter the water barely stays above freezing and the air gets even colder. The raw material arrives as briquettes or ingots weighing 44,000 pounds each. They're loaded into powerful electric arc furnaces with a 440,000-pound capacity. Giant vessels 30 feet tall with graphite electrodes 24 inches in diameter. Steel for these hooks comes primarily from Scandinavia, where it's melted in vacuum furnaces with special composition control at every stage. The logistics are impressive even before production begins. 44,000-pound ingots arrive by barge right to the factory docks. If you're curious how things are made that human lives depend on in the open ocean, subscribe to the channel right now and hit that bell so you don't miss the next episode. When a current of up to 100,000 amps flows between the electrodes and the metal, it creates an arc about 20 inches long that heats the furnace contents to over 3,600 degrees Fahrenheit. This isn't just hot, this is the temperature where steel stops being a solid and transforms into glowing liquid. The furnace slowly rotates for even mixing, while gases are drawn off through powerful filters. The melting process takes 4 to 5 hours, during which the metal is purified through vacuum evaporation and argon purging. The finished melt, a bright yellow color, is poured into ladles lined with fire brick. The temperature at discharge, around 3,000 degrees Fahrenheit. Cranes lift the ladle and transport it to the casting line, where prepared molds are already standing. Massive steel structures weighing up to 200 tons each. The mold geometry is calculated accounting for 2% metal shrinkage. If you don't build in this allowance, the finished blank will come out smaller than required. They pour at a 45-degree angle to avoid air pockets. A stream of liquid metal about 20 inches wide fills the mold in 10 to 15 minutes. Then they seal it with a lid and move it into a controlled cooling zone. And this is where one of the most critical stages of the entire process begins. For the first 24 hours, the temperature drops only to around 1,500 degrees Fahrenheit. The next 2 days, down to 400 degrees. Full cooling to room temperature takes up to a week. Sensors continuously monitor temperature gradients at a depth of 4 inches. The slightest variation can cause thermal stresses that lead to internal cracks, invisible from the outside. During cooling, the metal crystallizes, forming a coarse structure that's later optimized through heat treatment. Workers in protective suits monitor the process through viewing panels, while automated systems record thousands of parameters every minute. The finished blank weighs between 100 and 200 tons, stretches up to 40 feet long, and measures up to 6.5 feet in diameter at the base. Once the lengthy cooling period is complete, the workpiece is pulled from the mold, using cranes rated for 300 tons and transported to the forging shop, a massive facility covering 22,000 square feet with ceilings 80 feet high. Here stand hydraulic presses capable of exerting up to 50,000 tons of force. That's not a typo. 50,000 tons of pressure on a single point. For comparison, the Eiffel Tower weighs about 7,000 tons. These presses push 7 times harder. The workpiece is cut into sections 20 to 26 feet long and reheated in gas furnaces to 2,200 degrees Fahrenheit. The metal glows bright red and becomes malleable. Workers in heat suits use magnetic grips to position a section under the press. First stage, rough deformation. The press descends with up to 10,000 tons of force, compressing the metal by 20 to 30% in a single cycle. Each strike lasts seconds, gradually transforming the cylindrical blank into the recognizable silhouette of a hook. Next comes intermediate forging. The metal gets stretched out, they shape cable holes up to 2 feet across and lugs 6 inches thick. The presses are equipped with complex dies made from high-strength steel, matching the exact geometry of the future hook. Total forging cycles, up to 50 per section, with breaks for reheating every 10 to 50 minutes. Between press strikes, they constantly flip and reposition the workpiece. This ensures even densification of the metal throughout the entire volume. Forging doesn't just shape it. It improves the internal structure of the metal, refining the crystalline grain and multiplying the strength compared to the cast state. The final forging stage, precision work on the working section. The main arc of the hook reaches over 3 feet in diameter, wall thickness, 12 inches, bend radius, 8 feet. The press dies work with accuracy down to a fraction of an inch, forming reinforcement ribs and flanges. After each strike, they blow off the scale with compressed air at 90 pounds per square inch. After forging comes heat treatment, a stage without which the hook would be just a pretty but unreliable hunk of metal. The piece is placed in a furnace for tempering at 1200 degrees Fahrenheit for 20 hours. This relieves the internal stresses built up during forging and gives the metal the necessary impact toughness. Then comes machining on milling equipment. Surfaces are ground to specified roughness. Mounting holes are drilled. Threads are cut into the attachment points. Each hook weighs between 50 and 150 tons depending on load capacity. Manufacturing takes anywhere from 3 to 6 months. The plant produces up to 20 of these units per year, and each one costs millions of euros. They go to crane companies that install oil platforms in the North Sea, the Persian Gulf, and off the coast of West Africa. Now here's where it gets really interesting: ultrasonic testing. This is where manufacturers hide a detail they'd rather not talk about. Every hook gets checked for hidden cracks. Sensors scan the metal with a 5 MHz wave, detecting defects as small as half a millimeter. If even one microcrack shows up, the part gets scrapped. No negotiations, no exceptions. Why is this so critical? Because these hooks work in conditions where failure isn't an option. An offshore crane lifts a platform section weighing 8 to 10,000 tons to a height of 100 to 130 feet above sea level. Waves slam the vessel's hull, the crane sways, the load cycles constantly, slackening slightly, then building again. These cyclic loads are especially dangerous. They make cracks grow even when the overall stress stays within design limits. Under these conditions, a microcrack that slipped past inspection turns into catastrophic failure within weeks. That's why every hook gets tested not once but multiple times. Ultrasound, X-ray, magnetic particle inspection, load tests up to 120% of rated capacity. After passing all inspections, the hook's surface is coated with an epoxy layer 200 microns thick to protect against saltwater corrosion. Then they apply the markings: serial number, steel grade, manufacturing date, and load capacity. This is the hook's passport, which will follow it throughout its entire service life. The global fleet of offshore cranes exceeds 4,000 units, of which around 1,200 are floating vessels with lifting capacities above 5,000 tons. Hook production for them is concentrated in Europe, primarily in the Netherlands, Norway, and Germany, and SN total output across the entire industry comes to just a handful of units per year. The finished hook is loaded onto a specialized platform and shipped to the vessel. There, in the open ocean, they'll attach a cable to it, hook a platform section to that cable, and this piece of forged steel, born from molten scrap, will single-handedly hold the weight of several hundred railroad cars. Waves, wind, rolling seas, and it holds.